Okay, so let's start.
The following message is best viewed on an oscilloscope.
Okay, shall I start now?
Yes, I suspect Janglai is, so his video is frozen.
Okay, so.
But I think I'll do the introduction and then we can start. It's just to warn all the speakers what's coming up. Janglai, you're available now? Okay, I'll do the introduction and then we can start and then we swap roles for today as conveners. So I'm Caterina Dognoni and there's also Janglai Liu, and we are the conveners of the Dark Matter session, and we welcome you to this last parallel session on dark matter. There's still also the poster session after this. And for all the speakers, we have done our best to try things in advance, but small things can happen, so don't worry about that. And we will signal the 2 minutes before your talk by writing on your slides. So if you look at your screen and see 2 minutes left, then that means that there is that you have 2 minutes left. And their talks are 20 minutes with 5 minutes of question and answer. So the first talk we have Andrea Caputo, that you can now share the slides if you'd like.
Yep, so sure, let's see. Can you see my full screen?
Perfect, yes. Thank you very much. So yes, please start.
Okay, thank you, the organizer, for the possibility. I'm Andrea Caputo from the University of Valencia. I'm finishing my PhD and then I will start in October, hopefully, at Weizmann and Tel Aviv University, my postdoc. And today I will be talking about an effective field theory approach to detect light dark matter in superfluid helium. And this work is based on this bunch of papers. And I want to mention in particular between my collaborators, Angelo Esposito is a postdoc in Lausanne, and my professor in Rome, Polosa. This is the outline of the talk. So I will introduce you the effective field theory ideology that maybe not everyone is familiar with. Then I will introduce the effective field theory in particular for superfluid helium and dark matter interaction. Then I will show the results and conclusion with future plan that we are working on right now. Okay, so first of all, the effective field theory approach is based on some very fundamental pillars, very simple ones. So first of all, we will be agnostic about the macroscopic dynamics of our system. And this actually is very good when you don't know how to describe the macroscopic dynamics of your system. This will be the case for superfluid helium, that is a strongly interacting system that you don't know how to describe. Then, so because of this, what you do, you focus on low energy, like soft, long distances, degrees of freedom, and symmetries. And because of this, what you do, you do your theory, you organize your Lagrangian in a derivative expansion, right? You can think about the Gaussian theorem for this. And so this is the picture that you have to have in mind. Well, so we ignore the UV dynamics, let's say. More technically, what we will deal with, because we want to study the interaction of dark matter with some detector, right, superfluid helium, we deal with the effective field theory of a condensed matter system, like a detector. So every condensed matter system actually is very peculiar because it breaks Lorentz invariance, like in Poincare symmetry, generically. We know that we need to have a theory that, generically speaking, will be Poincare like Lorentz invariant. So what's happening, how we describe this, is that we say that the states of a theory, not the theory itself, is breaking the symmetry. So we speak about a spontaneously breaking of the space-time symmetry, okay? And every condensed matter system realized that, you know, if you look around you, the chair that I'm sitting on, right, it has like a preferred frame. So it's breaking boost, for example. It's also breaking rotation, for example. So once that you break spontaneously your symmetry, you will have Goldstone theorem that is telling you that you will have soft degrees of freedom, right? Describing your system at low energies, and these are the Goldstone bosons. So what you have to do, you have to identify your Goldstone bosons, you identify the transformation under the symmetry group, and then you write down your Lagrangian and you do a derivative expansion as usual. The only caveat here is that we have a breaking of a space-time symmetry. So it's a little bit more difficult to identify the Goldstone, etc. But it's like just technical. So I won't give too many details about that. But the idea is very simple. So how this works, for example, for superfluid helium, okay? So superfluid helium for an effective field theory approach is just a system, a condensed matter system with an extra U1 symmetry that is essentially the conserved number of particles, okay? And then what it does, the system breaks boost, as I said, for any condensed matter system like that. Then you also break this extra U1 symmetry, and then you also break time translation, okay? And this theory actually, we were not the first one to write this theory. Son in Chicago wrote this, and then also Alberto Nicolas at Columbia University and collaborators work on this. So you break the symmetry, and what you do is that you preserve a combination of the Hamiltonian and this U1 symmetry. So here Q is the generator of this U1 global symmetry of the superfluid, and mu is the chemical potential of the superfluid. So what I'm saying is that essentially time translation are broken, but there is a combination that generate unbroken time translation, and this is the Hamiltonian that generates that, okay? And then to implement this, what you do essentially is that you have a real scalar field. This is realized non-linearly your symmetry, so it's shift under this U1 symmetry, and then it acquires a VAV that is time dependent. So you see here the VAV that is essentially with mu tau, so it's time dependent. So you break time translation, obviously, but because also of the shift symmetry, what you preserve this combination H minus mu Q, okay? So what you do, as usual, like for example, like you do in the Higgs mechanisms, you have your VAV, you expand in fluctuation around your VAV. Your fluctuation are the Goldstone fields, and the Goldstone fields in the superfluid helium are phonons, So the phonons of the U1 of the superfluid helium are nothing else than Goldstone fields of this breaking of the symmetry, of this U1 symmetry. And so this is the spectrum of excitation in superfluid helium. So this is the momentum, and this is the energy of the excitation. So you see here, this is the region, this linear region here of the phonons, okay? And this is the region that we will describe with our effective field theory. This is important. So this region, you have gapless excitation, as you can see. So the energy goes to zero for the momentum that goes to zero, okay? And actually, there is this linear relation with the speed of sounds as a coefficient. Okay, the speed of sounds for superfluid helium is something like 10 to the minus 6 natural units. And then I also noticed that there are other excitation, for example, rotons, but our effective field theory will not capture that. And I will come back to this for our results. And this is an important point, okay? And then, as I said, what you do is you know your symmetry, this U1 symmetry, okay? So you have to write your Lagrangian that is invariant under the entire broken group because the symmetry breaking is spontaneous. So you realize that there is this invariant at lowest order that is very simple to build actually. When that you work in a covariant framework, how do you build a Lorentz invariant theory? You just contract indices, right? The mu phi, the mu phi. And then you have to have the shift symmetry of the U1. So you have derivative coupling, okay? So you have X, that is your invariant, and then your action, where bulk means the bulk of the superfluid, will be a function P, generic function P of your invariant, okay? At this point, P is just a generic function of your invariant. Actually can be showed with calculating the stress energy tensor that P is the pressure of the superfluid. So the name is not, is not casual, is the pressure of the superfluid. And so what you have to do, remember that psi, this field here, was expanded around the valve, right? So you will have the valve plus fluctuation. So what you have, you will expand, Taylor expand your Lagrangian, okay, in small fluctuations, so in your phonon fields around the valve, and you will get a Lagrangian, okay? A Lagrangian expanded in the photon field, in the phonon field pi, okay? So this is your Lagrangian. The coefficients of your Lagrangian is also the nice and bad thing of effective field theory, right? You cannot predict your coupling because you don't know the UV dynamics of your theory. But what you can do, you can just fix by experiments because they are all related to the pressure, the derivative of the pressure respect to the chemical potential. So these coefficients at leading order are fixed. And then you have your Lagrangian. So you see, for example, this Lagrangian. You have here, as an example, this vertex, right? So you have the three phonon vertex, and you can calculate your Feynman rules, you can calculate your amplitude, and it's all very straightforward, okay? And then, now I have a description for superfluid. So I just talked about superfluid. There's nothing new, people already did it. What we did actually after was to go to next leading order, but I won't talk about that. But now we have to add dark matter, right? This is a section about dark matter. I actually don't want to spend too much time about dark matter because, I mean, generic dark matter, because you know very well about this. I just want to say that we have a very broad range of dark matter masses that we can explore. In this work, we focus on what is usually called light dark matter, like sub-MeV dark matter, that is very hard to detect with usual deposit energy dark matter like xenon, super CDMS, dark side, or the others, because the smaller is the mass of the dark matter, the less energy you deposit, right? So it's very difficult to detect. So you have to think about new ideas to detect light dark matter. Superfluid helium is a very nice idea because the nucleus is light, and also because, as I show you, the phonons are gapless. So in principle, it's free to excite them. Of course, the problem then will be to detect them. And this idea was actually pioneered the first time by McKinsey and Guo in Berkeley. And actually then after that, a few years after that, Catherine, Caitlin, Simon, Tongyan did a lot of great works theoretically studying it. What I will show you is that we have other techniques to study the problem that we think that are more suitable to make prediction, at least for a particle physicist, for the theories that now knows like QFT. And so you have your dark matter chi. You can write a generic interaction with superfluid. Okay, so for example, you can write an interaction with the density of superfluid. This is also what Catherine, Simon, and the others did in their work. And we will be an invariant of the X, like the invariant that I showed you. So you do the same stuff. You expand your Lagrangian, okay, and fluctuation around the bath. So you will have coupling between the dark matter chi, that in this case we took to be a scalar, and the phonon field. Okay, so you will have, for example, a Lagrangian that looks like this. So you see here you have the dark matter, and then you have stuff with the phonon field pi. So this Lagrangian is giving you the interaction and the Feynman rules for the interaction of dark matter. When the dark matter arrives, it scatters on the superfluid, it interacts, and it can produce phonons. Okay, and then G chi is the coupling that you want to determine with your experiment. You want to measure for a given dark matter mass. The nice thing is that with this Lagrangian, you can really calculate whatever you want at this order. For example, these are the diagrams at leading order for the production of two phonons. And it's very simple. I gave you the Lagrangian. It's a very nice work for the PhD or even a master student. You open your Peskin, you calculate your amplitudes, and then you can calculate whatever you want, 1 phonon, 2 phonons, 3 phonons, whatever you want. And this is done with standard QFT computation. And actually, for example, with the QFT computation, we reproduce the phonon decay that is usually obtained with hydrodynamic techniques. So our approach is kind of very similar to that. While that one, for example, is not reproducible easily with the Hamiltonian approach that was taken by the Berkeley group, let's say, right? That is based more on the fact that you rely also on condensed matter techniques, and you take some structure function of the superfluid helium, and then you use that as an input, right? So I think that you have less control. While in our approach, you can really calculate whatever you want, at some order, of course. And so, of course, now what you can do, you can calculate the production rate, right, of your phonon or two phonons. Then you have to detect them. I'm not an experimentalist, of course, but if anything is interested also in Europe, I know that there are groups in the United States that are interested to this, but it will be very nice to really try to implement these experimental details. The two experimental techniques that usually we have in mind is quantum evaporation. So just the phonon is energetic enough that the single phonon travel up, it hits the surface of superfluid helium, and it can extract an atom. And then is energy release. So essentially you produce all your phonons as an energy that is large enough to be detected with calorimetric techniques or even with tests and all these nice techniques that now are reaching very, a very good precision. And there is a lot of work to do on the experimental side. So our work is mainly theoretical. And so here is some of our results. So essentially, here is the mass, and here it is the cross section. So it's related, if you want, to the coupling G chi that I was talking about. The green line is the one phonon process. So dark matter arrives, and in your Lagrangian, you will have a vertex with chi pi, the phonon. You can calculate the ray, and actually this you can detect just with quantum evaporation. There is some kinematical threshold, and you cannot go because you have to conserve both momentum and energy, and the speed of sound is very low for superfluid helium. So actually, in order to detect it, you have to go to larger mass than 1 MeV, okay? So this is why here there is this cutoff here, so this is a one phonon line. And then here instead, the blue line is the two phonon emission. So these two diagrams here, okay, is the two phonon emission. You can calculate the rate, and this exclusion, all these exclusion plots are essentially like having 3 events per kilogram per year, and detected then with quantum evaporation for one phonon and energy release, so above 1 milli-electron volt for the two phonon. And you can notice some interesting stuff. So with our approach, the blue line, we reproduce almost like perfectly the black line, the dashed black line by Kathleen and Catherine, that was obtained with standard condensed matter techniques that, at least to me, are more difficult to understand. And now I come back to the point that I was telling at the beginning. Our theory doesn't include maxon or rotons. So in their paper, actually, Kathleen and Simon and the others were claiming that rotons are important. So what we see with our theory actually is that the main contribution is really coming from phonons. And this is very important even experimentally. If you want to do an R&D and do your experiment, it will be very important and crucial to understand what you're going to detect, right? And the effective field theory gives you a very powerful tool to do that. Another thing that is very peculiar is that here in gray, you see the pure phase space. That is to say, you take your amplitudes and you put your form factor to 1, no momentum dependence, right? If you do that just for phase space, you have a huge enhance of the rate, and so I drop here of the limit of the cross section, I drop in the positive sense. So what's going on? There should be some physical intuition, right? And the physical intuition is that essentially the physical motivation is that to maximize the energy release in the two phonon case, what you have is that you produce the two phonons back to back, and in this limit there is an exact cancellation of the two diagrams that you produce here. And you can see this also in the approach. Actually, Simon and Caroline and the other, they saw this, but you have to go to this lengthy computation and it's very demanding. In our approach, it's actually just due to symmetry. So you have this U1 symmetry, you have your word identities, and then you can notice that because of the specific coupling with the density, where the momentum goes to 0, you have that also your matrix element goes to 0. You can look at the details of this very simple proof in this proceeding by me, Angelo, and Antonello Polosa. But the very thing that I want to stress is that really this is due to the coupling with the density of the superfluid helium. It's true that actually, if I want to be honest, this is I think that you really have to work hard to imagine a theory in which the coupling is not with the density, but in principle you can. And if you do that, for example, you think to couple it with pressure or whatever you want, then in principle, the results can be quite different because at low mass, you don't have this huge kinematical suppression, okay? And so this is also a very powerful tool for our approach. Another very nice thing, I think that, you can come to me, you can drop me an email and say, look, I want to study this model. Can we work it out? And it's very nice. It's very, it's something that I like. For example, you give me your model, or I have my model, for example, in this paper here, always with Angelo, Hemma, is a fantastic now PhD student in Heidelberg, and other collaborators. We studied a model in which we were not agnostic anymore about the mediator. We have a dark photon in our theory. So what you have to do, you have to write your theory. And now as a byproduct, we also wrote down for the first time the effective field theory of a photon also interacting with superfluid helium, and then also a dark photon, of course. Now, what you have is that you have to introduce new coefficients, AX and BX, and X, remember, is always the invariant of your superfluid helium theory. And these coefficients are essentially related to the polarizability of your superfluid helium, because actually the helium is neutral. So you have to go to higher order in your multiple expansion. So these are essentially related on the background on electric and magnetic susceptibilities, but you can fix them again, experimentally. So again, you have your Lagrangian, you can do your calculation. And what we did was to compute the most suitable process, that is the production in this case of one phonon, but now with an external electric field. Because you notice here in your Lagrangian, you can notice that you have, for example, here vertices when you have two f mu nu, right? So two phonons. So one of them you can put a quanta, right? Your photons, and the other one will be your external field, right? And then if you do that, you can enhance your process, your production of phonons. And this red line is our reach with quantum evaporation. And you can see that actually, as usual, the superfluid, you can go to lower masses. Now, honestly, the prospects are not the best one. This model is not the best one in the sense that the reach is already excluded by BBN, nucleosynthesis, right? And you're not in the ballpark of freezing, but this is typical, right? Freezing is very small coupling. And BBN is also very powerful when you go around MeV or lower. But I mean, in my opinion, it's always good to have terrestrial probes, right? If we don't have terrestrial probe, we will never say that we detected dark matter. And actually, if imagine that we detect dark matter, then we will have to think again about our cosmology, right? Cosmological theory. So in any case, I think it's good to think about that. Okay, now it's 2 minutes left, but actually I already came to my conclusion. And so superfluid helium is a very nice possibility. There are a lot of experimental details to work out. So if anything, of you is interested, we were trying also to look in Europe to experimental groups. And but in order to also to implement experimental details, it's very important to have a theoretical control of what's going on. And I think that effective field theory is good for this, especially because it speaks the language of us, right? Of high energy, of my community, at least, like high energy physicists, right? And there are a lot of future direction. Right now, we are computing the free phonon emissions, and we're including, for the first time, excluding order correction in your Lagrangian expansion. And of course, you can study, for example, other systems, superconductors, crystals. There was a very nice talk by Simon Knappen a few days ago. And Angelo, also my collaborators with Tom, Melia, they already studied like bidimensional solid. So it's a very rich field, I think. And you can ask me a question now, but you can also drop me an email if you have ideas, if you have questions, and I will be very happy to discuss with you. For now, just, thanks a lot, and please ask questions.
Thank you very much for your talk. Thanks also for staying on time. Sorry, my camera doesn't seem to work this morning, but I'm sure you'll be fine. So are there any questions for this talk? We have time for a couple. So Zhanglai?
Yeah, maybe I'll try. How's my network now? Is it working?
Yeah, it is.
Yeah.
Okay, wonderful. Okay, thanks for this very interesting talk. I have one confusion, maybe you can help me, which is that although you say gapless, but the one phonon actually probably cost 0.6 milli-electron volts of the energy. So why you have a figure showing that the threshold of including the two phonons seems to be even lower than the one phonon exchange?
No, but when you have, when you have one phonon, right, you don't have, so you have to conserve momenta, right, and energy. So you don't have a lot of possibility, right? But then when you have, imagine that now you have two phonons instead, so you can work in the limit in which you are like back to back. So you are trivially like conserving momentum, like going back to back, right? But then you have much more space for the energy, and you are suppressed by the speed of sound. Remember, the speed of sound is very low. So you have, when you think about phonons, you have the cutoff that is 1 keV, right, for the momenta of your effective field theory, but you can go lower than that, right, with your phonon. But then when you are on shell, the energy associated with that phonon will be CS, so 10 to the minus 6 for the momentum. If you are back to back, the momentum can be very small, and respect to that, the energy will be 10 to the minus 6 that. So this is why you can go even lower. Then of course, at a certain point, if you go too low, the kinematical region in which you go to zero momentum is very small, so you are cut off anyway, right? But in principle, when you are back to back, this is the energy in which you enhance the energy release because of this, essentially.
Thank you.
Thank you for the question.
If there's no other questions, I have one. Can't raise my hands, so my question is, you say that EFTs speak the high energy physicist language, which is correct. We used to love EFTs, but people that had other experiments didn't necessarily see how at least high energy colliders, maybe low energy colliders, the problem is less, can be connected to low energy experiments, both because of EFT validity issues, but also because of the big difference in energy scales that you have when you consider the interaction, right?
Absolutely.
So in the plot that you showed where you have the Sensei limits and the helium-4 limits, I'm thinking you could potentially have a bar limit there, or something that has like an electron-positron invisible signal, where you don't, where the dark matter particle is so boosted that you don't really care, like you can always produce it. So this limit would go down to very low MeV. What are the caveats in doing that? This is maybe more of a general question.
With colliders, actually, I really don't know, because I didn't work too much about colliders. Generically speaking, so Babar, for example, I really don't know the details. With dark matter is always the same stuff, right? So with collider, I really don't know, but with dark matter is just the usual energy issue, right? That you don't have the threshold to detect it. Like if you think about xenon, if you think about even super CDMS, right? And for collider, in principle, I think that yes, you will have also there some maybe background rejection or whatever that you have to care about. When I took this plot, actually all these bounds, I was taking that from paper by Tomer, Volansky, etc. in this light dark matter limit. And it will be interesting, like from the collider point of view. Regarding the effective field theory, more generally speaking, like, you know, the issue of effective field theory. One issue of the effective field theory is that, of course, you cannot predict like the coupling, the UV dynamical coupling, right? And also that you cannot include, but we are aware of that, but I think that is the important point. We cannot say anything about the high energy physics, right? As you correctly said, like protons, for example. But actually that could be important. So if we were to find, for example, that our prediction was like factors away from the one done with Hamiltonian dynamics. So just also to stress like the Hamiltonian dynamics, because like maybe people don't know, but what you do there also is that you do, with superfluid helium, you do experiments with neutron scattering. So you make a neutron scatter on the superfluid helium, and then you measure some response function depending on the energy and the momentum of the excitation that you produce, right? So, and that is what you call the response function. And the dark matter is very similar to neutron, right? There are two caveats here. So first of all, people, to do that, neutron, as you know, they're like GeV mass or so. So you have to extrapolate when you go to very low mass of dark matter, first of all. So you have to extrapolate the response function. And you really don't know you don't know very well which excitation are contributing to your response function, okay? So you can think about the fact that, maybe rotons are very important. Then experimentally, you will have to think about your experiment. What we show with effective field theory, we are perfectly aware that you cannot describe those interactions, right? So we will be blind to that. But we find that the rate with phonons is essentially that one. So under this point of view, effective field theory is powerful, very powerful tools. And there was actually recently also a paper by Gordon Baim, and he's an extremely known condensed matter physicist. And they were also studying like power counting expansion and superfluid helium dark matter detection. So in this regard, at least for low energy, given that, for definition, you have low energy experiment, I think that effective field theory is very, very suitable. Then for collider, of course, as you said, it's also different. Also because, like, if you think about this math, right, all the effective field theory of colliders, you have really, really a lot of possibility, especially if you introduce flavor, right?
Yeah.
While here, a leading order.
Maybe, given the time limit, maybe we should leave this discussion to matter most.
Yeah, I'll probably send you an email because also, with your collaborator as well. Thanks.
Yeah, cool. Thank you.
Very good. So let's move on to the second talk. Could you, okay, great. So the second speaker is Seguk N, and he's gonna talk about the search of the axion dark matter in the mass range of 6.62 to 6.82 micro electron volts. So please go ahead. Can you share your screen, please?
Okay, thank you. Thank you for.
Very good. Please go ahead.
Mm-hmm. Okay. Can you see the screen?
Yes, very well.
Oh, thank you. Hi, my name is Taebyok, and I'm a graduate student in KAIST in South Korea, and I'm working with this gentleman from IBS CAPP. So before my talk, let's briefly talk about our center. Our center is called CAPP, stands for Center for Axion and Precision Physics, and it's located at Daejeon, South Korea. And as you can see this picture, we have 4 parallel axion search experiments in a variety of mass range. And one of them is CAP-ATB, which I am working for. And we recently published a result of axion search within the mass range of 6.62 to 6.82. And it's equivalent to 1.6 to 1.65 gigahertz of frequency. And this photo is our the entire system of ours, and this is our exclusion plot corresponding to our results. So let me briefly talk about axion first. Axion is arising from the strong CP problem, and it's the solution of strong CP problem actually. And we can see the strong CP problem by measuring the neutron EM. And the recent measurement shows that it's less than 1.8 to 10 to the 6 minus 26, which is very small. And we don't know why it should be small. And that's called the strong CP problem. So Pechai and Kim in 1960, they employ a global chiral U1 symmetry, or we called it as U1 Pechai-Queen symmetry, and axion is a result of breakdown, spontaneous breaking of U1 Pechai-Queen symmetry. And at earlier stage, the axion ruled out in the very high mass region, but still so-called invisible axion survived with 2 benchmark model, KSVZ and DFSZ. And it has very long lifetime and very light and long lead. So it's also a promising candidate for the dark matter, specifically for the range of 1 microelectron volt to 3 millielectron volts. And the effect, so-called Skivy's effect, we employ a cavity resonator to detect the resonant conversion of axion to photon in a cavity resonator, immersed into a static magnetic field. So the axion haloscope means detection is to detecting the axion around our galaxy, and we can actually calculate the power of axion to photon conversion in a microwave cavity. Here, this equation where Ga gamma gamma is axion photon coupling strength and some other experimental parameters. You see there's this magnetic field term here. So we have to have a very strong magnetic field, usually 8 Tesla or even more than that. And there's form factor, which I will talk about it later. And we have a Q factor as an experimental parameter, and beta, which is the resonator mode coupling to the load. And the dominant noise source of our system is generally the thermal noise or shot noise from the amplifier. And those two are independent from each other. So we can just add in terms of, we can just add it. So there are two major noise sources, the amplifier noise and cavity. And here the cavity noise temperature is is white. That means it's flat over the frequency, but TA is not trivial, so we have to measure it very carefully to estimate our figure of merit, which is called signal to noise ratio. So signal to noise ratio in axion haloscope is defined as the ratio between the axion to photon conversion power divided by fluctuation of noise. And the fluctuation of noise is inversely proportional to the number of spectra averaged, because we're going to average the spectra in with a very large number. So this is the signal to noise ratio. I'm going to talk detail later. So firstly, this is our microwave cavity, which has about 3.5 liters of volume. And among so many modes in this cavity, we employ TM010 mode because it maximizes the form factor among any other cavity modes. And we can estimate its resonant frequency specifically for TM010 mode, and it's calculated as 1.7 gigahertz, which is very which is in a good agreement with our measurements. And the Q factor at the low temperature is around 110,000. And we employ a split design because of this, because the cavity is in a very strong magnetic field, and even a very small vibration causes the eddy current, and it generates some heat that hits the entire system, especially for the cavity. And you can see the effect of eddy current by comparing between conventional and conventional design and the split design. And this is our frequency tuning mechanism. Firstly, we employ a dielectric tuning rod, as you can see here. So we put this in the cavity to alternate the form of electric field inside the cavity. So it breaks the symmetry, spatial symmetry of the modes, so the frequency changes. So the overall frequency range of our cavity is around 1.4 to 1.7 gigahertz. And we study with simulations and measurement, and there's no mode crossing throughout the range. Mode crossing means the two mode, the frequency of the two mode cross each other so that we cannot actually distinguish them. And we employ this type of very unique material to connect from room temperature to our cavity. That's because we have room temperature motor to rotate the tuning rod. So this CFRP tube has very low thermal conductivity, so it doesn't affect in terms of heat in our system. And as a result, the frequency tuning tolerance is achieved to around plus minus 5 hertz, which is the beam size of our analysis. And our magnet is superconducting magnet with a nylon titanium wire. And we have a compensation coil here. So the magnetic field around the mixing plate is around a few hundred Gauss. And the maximum B field is 8 Tesla, but we average the B field over the cavity volume, then it goes to 7.3 Tesla. And this is the definition of form factor. You can see there's a E field and external B field coupling, and the strength of magnetic field energy here. So form factor is generally the alignment between E field of the mode and external B field, and we can only acquire it from, we can only calculate it from the simulation because we cannot measure the electric field profile very precisely. So if there's a TM00 mode and uniform B field with perfect alignment, then this gives form factor of 0.69, but generally we have a tuning rod inside and there's some other error, or there's other source that that degrades the form factor, so it's generally less than 0.69. And you can see the frequency dependence of form factor in our cavity. And after that, I'm going to talk about antenna coupling. The antenna coupling is defined as the ratio between cavity Q factor and the antenna Q factor, so that we can have this relationship. So if the coupling is strong, then the loaded quality factor decreases. And there are several ways to measure it, but so far the most precise way to measure it is by looking at the Smith chart, which is the in here, x-axis is the real part of the reflection coefficient, and imaginary part for the y-axis. So after we take the data, we fit the Smith chart with the circle, and we get the diameter to get the effective antenna coupling. And the tuning of antenna coupling is important, is because beta equals 2 is optimum for the scan rate, which is defined as the cavity loaded bandwidth divided by total integration time. So during the physics run, we maintain the beta from 1.8 to 2.0 so that we can optimize the scan rate throughout the range. And this is our receiver chain. As you can see here, there's a microwave resonant cavity. There's a circulator to measure different experimental parameters from the cavity. And here we have a first stage amplifier, which is located at 1 Kelvin. And typically it has less than 1K of effective noise temperature. We have the total system gain of 132 dB. The reason why we have so large gain is because the Axiom photon conversion power is very low. It's less than typically around 10 to the minus 23 watts. So we have to have such high gain in order to detect it. So the noise coming from the whole system generally looks like this, a very smooth curve with a fluctuation. And this is after the large average, about it's 20,000 average spectra. And we analyze noise by employing the equivalent circuit between cavities and amplifiers, so that we have resultantly this kind of equation, which is firstly introduced by ADMX in the paper published by ADMX. And these are the big parameters. So after that, we try to measure the noise and the total gain more precisely with the noise spectra. So we use the cavity as a noise source, and we change the cavity temperature from 50 to 200 milli-K, and we compare those two to get the total gain of our system. The gain is simply can be measured by this formula, where pH and PC is the noise power on resonance from hot and cold. And this is the cavity effective noise temperature. And this is roughly the same with the physical temperature of the cavity. So from this formula, we can get the total system gain of 132 to 135 decibel. And the corresponding noise from noise is around 1 Kelvin. So after that, we try to set our scan parameter. Firstly, we set the target sensitivity of 4 times GA gamma gamma, which is a KSVZ coupling, which is slightly above or down to QCD upper band of Axiom. And target SNR is set to 5. And firstly, we set RBW to 20 Hertz for optimization of DAQ efficiency, which is 46%. That means the ratio between the ideal time we acquire the number of spectra and to the total time we spend for a step. And span is firstly set to this weird number, and this corresponds to 3,025 points per spectrum. And after that, after acquiring the spectra, we merge the beam to get RBW equals to 500, which means that we merge 25 points, adjacent points. And resultantly, we have 60 kilohertz span and 121 points. And frequency tuning step is 220 kilohertz. You see the distance between center is 20 kilohertz. And this is set by optimizing the number of spectra to for the optimization for SNR when we overlap the number of spectra, overlap the spectra. And as I said, the number of spectra for a step is 12,000. And we separate the step 400 average times 30. So we acquire 30 average spectra, each of which is averaged 400 times. So these are the analysis steps. Firstly, we remove the baseline with 5 parameters fit introduced in the previous slides. And then we merge 5 bins so the intermediate RBW is equal to 100 Hertz. And we filter the spurious peak, which exceeds 4.5 sigma. And after filtering these peaks, and we merge 5 bins again so that the final RBW is 500 Hertz. And we try to make a pole distributions to get the Gaussian statistics of, to see the Gaussian statistics of our spectra. Yeah. And after that, you can see there's an overlap here. So we merged 3 bins with inverse variance weighting method. And then we can get a single spectrum and do the horizontal coating. We merged 10 bins corresponding to 5 kilohertz, which contains 99.9% of our axion power. And after all these analysis steps, we can get this nice Gaussian histogram with some axis here, which is, and we set the threshold to 3.718 and corresponding to 36 candidates to rescan. And we rescan it with a large number of average, then no one survived. So this is the result. We reached the sensitivity down to QCD axion band in the mass range of 6.62 to 6.82 with upper limit on coupling at 90% confidence level. And we're now preparing the extended scan, which is around 6.2 to 6.62 microelectron volts as a phase 2. So our center is preparing a lot of result. For example, here we have high max axion search with multiple cell cavity, 12 TB. They plan to reach down to DFSZ level of sensitivity. We have CAPACE, which employing JPA for quantum limited noise. And we have ATB, our projects, which we're preparing the extended search for axion. So stay tuned, and thank you very much.
Thank you very much. Very nice talk.
Thank you.
Are there questions? Let's see if there are hands up. We're waiting. Can I ask a quick question? So how is the gain, absolute scale of the gain calibrated? You said you measure power, but then how is the scale set?
You mean the here the scale? I mean it's here it's a low decibel scale. So if you convert it like then it's 10 to 13 absolute in absolute range. It's around 10 to the 13 of gain. Is that?
Sorry, yeah, this may be a technical question, but maybe I'll let Hugh ask the question. He has a hands up, please.
Thanks. Can you go back to the limit curve or the final plot?
Here.
Yeah, I mean, do you guys, what could you go deeper? I mean, how realistic is it to go lower to get all the way through the DFSZ, for example?
Here.
Yeah.
We have a firstly, it takes like more than 100 years to get to reach the DFSZ for like 50 megahertz of scan, I guess. So it's very hard for us to reach DFSC for now. And we have another problem because if you average heavily, then it doesn't follow Gaussian statistics anymore. So I guess we have another issue for that. So for now, we cannot simply reach that sensitivity, but other teams are preparing for that.
Thanks.
Are there other questions? Okay, well, thanks a lot. So maybe we'll move on to the third talk.
Yeah, thank you.
Yes, so the third talk is about a larger experiment somehow, the Lux Zeppelin dark matter experiment. And he will start sharing the slides. Perfect.
Can everybody hear me?
Yes, thank you very much.
Okay, so yeah, I'll talk about LZ. So like many of us, we've been doing remote collaboration meetings. So this was our meeting a couple of weeks ago via Zoom. So, you know, it's been fun to learn how this works in great detail. And if you look very carefully, you can see just below the logo, somebody actually underground in their mask. So there are people working in the lab now, which is nice. And I'll talk about that a bit at the very end. So do a little bit of background, probably a review to most people in the room. So LZ is a type of detector, the two-phase xenon detector. So a two-phase xenon detector is basically a bucket or a cylinder of xenon where we put an electric field across the liquid. There's a liquid to gas interface at the top with a second electric field. And then the whole thing is viewed by two arrays of photomultiplier tubes. And so the idea is that the interaction in the xenon creates scintillation light. So this is prompt light. We call it S1. And it also creates ionization electrons. The electrons are drifted by the electric field through the liquid to the gas-liquid interface and extracted into the gas, where they go through the second electric field and are accelerated to create what's called proportional scintillation light, or we call it S2. And so the typical event has a small prompt pulse of S1 light. Then there's some drift time, and then you get a larger proportional or larger S2 signal, which is proportional to the number of electrons that were freed. So the nice features about these detectors are the excellent 3D reconstruction. We can get sort of millimeter level resolution. You get Z from the timing between the two signals, because that's the drift time. And then you get X and Y from the hit pattern in the PMT arrays of the S2 light. And so this 3D position reconstruction allows for self-shielding, which is hugely powerful in a liquid xenon detector to reject radioactivity and stuff around the edges of your detector. Another nice feature is that we can do particle ID using the ratio of charge to light. Basically just playing the S2 and the S1 signals off of each other gives us better than 99.5% rejection of electron recoil events, which is key for dark matter detection. So let me just sort of summarize in one slide why liquid xenon is a good target. So I'm just going to assume many people, again, are familiar with dark matter as a problem. So what are the things that we have to struggle with when looking for direct detection of dark matter? First, it's extremely rare. And so the solution that we've been coming up with over the last sort of 20 years is to increase the mass of our detectors to have more targets for the dark matter to bang into. And xenon is nice there because it's very dense. You can fit about 3 tons in a meter cubed. So liquid is just a very nice dense material, so you can scale it up quite easily. We are looking for very low energy depositions. And so you want low energy thresholds in your detector. And again, liquid xenon scintillates and releases electrons quite copiously. So you get something like 70 quanta per keV of energy deposited, which allows you to see these low energy depositions. Then of course there's backgrounds, which is the bane of all the dark matter experiments. So you have impurities, you have detector backgrounds, and then there are sort of internal backgrounds that are very hard to deal with. And so liquid xenon is nice because you can purify it as a noble gas. It's mostly easy to purify. The self-shielding is extremely effective. Xenon being so dense has lots of electrons, and so that gives you a low mean free path for most ionizing radiation, particularly gamma rays and betas. And then you can do discrimination again, which I mentioned earlier, giving you this particle ID by playing the charge to light ratio. So that's sort of a very brief summary of the liquid xenon TPC detector. And now I'll talk more about LZ. So LZ is going to be the next big xenon TPC and sort of the Lux and Zeppelin line of detectors. And it's going to be located in South Dakota. So the picture on the top here is the Homestake mine, which was an old gold mine that operated for 100 years in this town in South Dakota in the Black Hills. And LZ is located down at the 4,850-foot level, about a kilometer and a half underground, which is also where the Dune experiment will be going to reduce the muon flux by about a 10 to the 7 factor. So this is a 3D CAD model of the LZ detector, although it looks like my fonts have not quite made it through. But you can see a central TPC in the very middle that contains 7 tons in the central TPC. That's all contained in a cryostat, and then there's an outer detector, which is shown in green here, surrounding it. The outer detector is filled with gadolinium-loaded liquid scintillator to tag neutrons to reduce backgrounds. That whole thing sits in a water tank, again, for shielding purposes. And then there are various instruments and process systems to send in and take out the xenon as it comes in and out of this detector. So a few design notes in the TPC. The central TPC is 1.5 meters right cylinder. And again, I've already mentioned it has about 7 tons of active liquid xenon. We expect to be able to fiducialize at around 5.6 tons. So that'll be a factor of 50 increase relative to Lux and something like a factor of 6 bigger than xenon 1 ton. There's about 500 3-inch PMTs split between 2 arrays at the top and the bottom. We're going to put in 50 kilovolts onto the cathode. The bottom left here shows a zoom in of that cathode connection, which was a subject of a lot of R&D done by groups at Berkeley and before that at Yale to make sure we could deliver this high voltage. And the top right shows a zoom in of the sort of grid, the top grid region where the anode and the gate are. So this is where the liquid interface is between liquid and gas. And it's quite a sort of tricky engineering challenge to make these grids work, especially over this large of a distance. And I'll show some pictures of that later. Okay, the veto, which I mentioned before. So there are 2 components to the veto. There is the so-called xenon skin, which is shown in blue in this picture. So the TPC in the center, of course, is at high voltage, but the cryostat that holds the liquid xenon is at ground. And so you need some distance of xenon to hold off that voltage. And xenon, as I've already mentioned, is very, very dense and has a very low mean free path. And so radiation, in particular gamma rays, will interact in that xenon. And so we have instrumented it as part of our veto. So we have a ring of 1-inch PMTs around the top, a few 2-inch PMTs looking around the bottom. And then the whole cryostat is lined with Teflon to improve reflectivity to maximize light collection. And then beyond the cryostat, as I mentioned, there's this outer detector, which is 17 tons of gadolinium-loaded liquid scintillator viewed by PMTs. And so the key here is to tag individual neutrons and gamma rays that may have scattered in the central TPC and then left the central TPC, and then on their way out, they will scatter again in one of these veto detectors. And so our requirement for the outer detector was to have more than a 95% efficiency to tag neutrons. And we plan to use this to characterize backgrounds in situ. And so we think this is a key component that would enable any discovery potential, because we'll be able to measure and characterize with some precision our neutron field, the neutron background that the detector is exposed to. And of course, neutrons are one of the backgrounds that really can mimic a dark matter signal. And so by measuring that, being able to really understand that veto, we will be able to be more confident if we do see something that might be a WIMP signal. So just to show a little bit the effects of the veto, this is simulated data, but it shows on the left a hit pattern in Z versus R squared of events, single scattered events in the detector, in the central detector. And on the left is if you have no veto, and on the right is once you add the veto, you can knock out a lot of those background events. You can see it's just a much cleaner spectrum on the right. And so the combined veto system allows us to expand our fiducial volume. And actually the left, if you were gonna sort of take your metric to be the equivalent level of background rate, the fiducial volume goes from 3.2 tons in the left to 5.6 tons in the right. So we get to increase our sort of our fiducial volume by something like a factor of 80%, which of course, given the cost of xenon, is something that's hugely attractive. All right, a quick word on purification, which I mentioned earlier. So xenon is a noble gas. It's generally easy to purify, but that doesn't mean it's completely clean. So we do circulate the xenon continuously. Our plan is to circulate through the gas phase. So we have a gas purifier at something like 500 liters per minute. This would turn over the full volume every 2.5 days or so. And we've now demonstrated in testing on site that we can get up to something like 600 liters per minute quite easily. So we've met our requirement there. Then I'll just mention briefly krypton removal. So for those who are familiar, krypton 85 is a radioisotope of krypton that, because it's also a noble gas, will not get purified by the standard techniques. And so for LZ, we remove the krypton before condensing the xenon into LZ via chromatography. And this takes place at SLAC. They've demonstrated 75 ppq in an R&D stand, and now they're up to production. But the way that this works is basically you pass your xenon through a charcoal column. The xenon tarries in the charcoal, whereas the krypton moves through quicker. And so in the red trace, you see a krypton pulse coming through, and then sometime later, the xenon comes through. And so if in the middle here, you sort of switch where you're sending your gas flow, you can decrease the krypton content in the xenon. And so that's being done at SLAC now. A few comments about backgrounds. And so at the top, I'll start referring to a few papers which have been posted by the collaboration. So nothing went into the detector without screening. We have something like 2,000 assays of materials using a series of germanium detectors, ICPMS, or neutron activation analysis. Just for an example, the cryostat is made of the most radio-pure titanium in the world and is producing less than 1/10 of an event in 1,000 days after cuts. And then these assays were supported by a significant serious QA, quality assurance campaign during fabrication and construction. So a similar, in staying with the example about the titanium, this was the cryostat. Early on in the fabrication of the cryostat, because we were screening welds as they were being done by the company making the cryostat, we found that they were elevating the level of radioactivity. What was going on is that the color code on the welding tips from the supplier was missing. And so they were using thoriated welding rods, which of course was not allowed by the spec. And so they were introducing radioactivity. So fortunately, we caught this with our QA campaign, and so it didn't become a problem. But this level of care was key to make sure that nothing came into the system that was contaminating it. Radon, again, for those in the sort of business, radon really ends up being the bane of our lives. It sort of, as a noble gas, again, it can spin around in your detector and get into your liquids. And then when it decays, its daughters can stick to your walls of your system. And in particular for LZ and other Teflon experiments that use Teflon, alphas coming from these radon daughters into the Teflon on fluorine will give you neutrons. And so we have two strict things that we worry about. We worry about radon emanation itself, and we worry about exposure to radon during construction. So the TPC was fully assembled in a radon-reduced clean room, and we had a requirement of something like less than 500 nanograms per centimeter squared, or less than a total gram of dust on all liquid xenon welded surfaces, which we met during construction. We also had to make sure that the plate on the walls was low to reduce the neutron component. If you're interested, the picture on the right is dust that was coming out of filters of not the clean room when it was in full operation, but early on during commissioning. And we actually emanated this dust to understand what the amount of radon coming out. We also emanated the various parts of the system. We had 4 screening sites in the collaboration, and again, all major parts were emanated for radon before assembly. So you put all this stuff together and you can come up with tables and plots of expected backgrounds. This was published in this article listed at the top right. So on the left, you can see the ER component. And on the right, you see the nuclear recoil component. So we have something like 10 to the minus 4 or less counts per kilogram per day per KeV expected. And that's dominated by radon 222 in the low energy region. So this is radon emanating out of detector materials and dust in the system, giving us this background. So that was this is what we expect to be our #1 background. In the nuclear recoil case, you can see how incredibly well, I would say, the detector screening campaign worked. So the detector screening is this solid red line. And it's sort of at the level of the atmospheric neutrino rate. So we're actually limited by neutrinos in the nuclear recoil case. And then at the very lowest energies, you see boron-8 neutrinos coming in as well. So if you put all this together, for total counts in the full exposure, we expect something like 1,000 counts of ER and 1 count of NR. And then after you apply discrimination, if you were going to do a sort of a cut and count type of thing, you end up with something like 6 counts of electron recoil events in your region of interest with half a count of nuclear recoils. So this is just an incredibly low background rate for a very large detector. This leads to a sensitivity. So you could simulate a 1,000-day run of LZ. The top blue sort of region, this is the ER band. So this is effectively the sort of radon 222 signal coming in. It mostly populates this ER band. A signal would populate more or less the red band down here. So this is the discrimination that I talked about earlier, where if I look at S2 versus S1, you can see a separation between the electron recoils that are the background versus the nuclear recoils that are the signal. And a 40 GeV WIMP would sort of populate this region of this plot right here. And we will be seeing, again, this boron 8 signal. So these are neutrinos coming from the sun that give you very low energy recoils. And so we'll be seeing a significant population of those down here in this sort of low corner. If you put that all together into a sensitivity plot, this is the classic dark matter plot of cross-section versus mass. Here is the current best limit in green from xenon 1 ton. And then LZ at the end of our 1,000 days, we would expect to push down by something like a factor of 30 on that to get to a minimum of about 1.6 times 10 to the minus 48 square centimeters at a 40 GeV WIMP mass. So a significant increase, and there is room for discovery between where xenon 1 ton finished off and where LZ will be turning on. We also have sensitivity to non-WIMP signals. So I'll just give a few quick examples. Neutrinoless double beta decay, of course, is a very interesting topic. We have in our 7 tons of active liquid xenon, a significant component of xenon 136, even if it's not enriched. So you can make some sort of statements given our background levels about the sensitivity we'll have to neutrinos double beta decay. And at the end of our run, we should expect to roughly equal the existing CAM-LAN-XEN limit, although with statistics, it could fluctuate up or down. And so that's without any dedicated enrichment. And if you enriched it, you'd actually do much, much better. You get another order of magnitude on the lifetime of xenon 136. ER searches have been very hot in the last few weeks. In particular, I'll just mention that these xenon detectors are sensitive to electron recoils for many different types of new physics, and in particular, things like a neutrino magnetic moment or solar axions or axion-like particles. We have a paper in preparation describing LZ sensitivity to these signals. And people have probably been paying attention that xenon 1 ton very recently posted a paper and have been giving a series of talks about a signal that they have seen or an excess that they have seen, which is consistent with an interpretation in these various models. So this is a plot that's going to come in the paper that currently is under preparation, showing our sensitivity to just one of these possible explanations, the axioelectric effect with this coupling GAE. And so the xenon result is somewhere in this range, and our sensitivity will be below that range, being a larger detector and a lower backgrounds. Of course, there are other backgrounds that xenon 1 ton acknowledges could be running around in their detector. In particular, tritium and argon-37 are ones that we are particularly worried about. And so we're now redoubling our efforts to understand how to constrain these backgrounds for LZ. All right, so that's good. I'm doing okay on time. So now I'll flash through a bunch of pretty pictures because that's what we all want to see, is how these detectors look in reality. So here's the picture round. So these are the outer detector acrylic tanks sitting in the water tank underground in South Dakota. So we would pull off this white stuff and you have these lovely acrylic tanks that will end up going around the cryostat when it's put into place in the center. These have actually been underground now for over a year. So they've just been waiting to be used. This is the detector itself. So integration started in December of 2018 at a surface assembly laboratory, and something like 13,000 working hours later in a class 1,000 clean room, but actually performed much better than that. And again, the reduced radon environment, we were able to bring tens of thousands of ultra clean, low background components together into this lovely detector here. So here's a few pictures. These are the photomultiplier arrays. Again, there's about 500 3-inch PMTs in these arrays. This is the skin, which I mentioned before. So we line the cryostat with Teflon to improve reflectivity. And then we instrument by mounting an array of 1-inch PMTs at the top and 2-inch PMTs around the bottom, which you can also see in this picture here, to instrument this sort of skin veto system. This is the grid production. So this was done at SLAC in Palo Alto. They made a dedicated grid weaving, sort of a loom. They made a real loom to weave these grids. There are 4 meshes that use about 75 or 100 micron wire that are epoxied into rings. And again, this was another serious QA program to make sure that these were mechanically and electrically resilient and to make sure that they were clean to keep any dust off of these grids. So on the left, the picture here is the building up of the field cage. And then you see the grids coming in on the bottom right. And then this is final mating of the top region, the extraction region, which is in gas, with the main field cage. This is an engineer named Jake Davis who works at the SURF laboratory during that key step. So this was the final detector put together. Again, there's a top PMT array at the top, the extraction region, which in the previous picture you saw being connected. The top skin PMTs is this array of PMTs that goes all the way around the top, the field cage in the center, and then the cathode connections at the bottom with the bottom PMT array at the very bottom. And then a whole mess of cables, which was potentially in some level the most difficult thing was managing all these cables. So this was lowered into the cryostat last summer and then brought underground, I guess late last summer, and then brought underground in October. And so the detector has been underground since then. The cathode connection was done underground. Here you can see them purging the whole detector with nitrogen. So they're actually in ventilators here, or to make sure that they are working safely. And this was done shortly before March of this year, or just the beginning of March of this year. I'll do a quick word on the circulation system. So this was a circulation test that was done to make sure that our circulation system was working as corrected. So there was a test cryostat, which you can see here. Again, the label seems to have dropped out. Everything else in the picture is part of the full circulation system. And that was tested and, as I mentioned, sort of met all of its specifications. This is a quick picture again of the cryo plant at SLAC. This is the krypton removal, just again to give a scale of what this whole system looks like. All right, so one slide, because my time is up. Current status, so we've made significant progress in assembly of the TPC. Circulation testing is complete and we're currently at vacuum. I'll say one thing about the pandemic. So we had to shut down the detector in a safe state in mid-March. And so there was no work underground for about a month and a half after March. We reopened, or were able to reopen at reduced capacity starting in May. And we've been ramping back up slowly since then, following the institutional, local, and national guidelines for safe, basically for safe operations, to make sure that we are socially distancing and following all the requirements to make sure that our workers can stay healthy. So here's a quick picture of status and schedule. So we're sort of halfway through 2020 now. We expect to be filling with xenon towards the end of this year with first science in early next year. All right, so just to summarize again, construction is almost complete. The TPC is underground, the final connections are being made. We expect something like a factor of 30 to 40 improvement in sensitivity on current best limits with discovery potential to a wide variety of non-WIMP physics. I haven't mentioned much xenon N ton, which I believe gave a talk the other day, but since both detectors are coming online, I think 2021 will be an exciting year for direct detection. So thank you.
Thank you very much. It's a very nice and promising talk for this field. Are there any questions? I see three actually. So I'll give the microphone first to Jochen. I don't know who came first between Yang-Lai and Jochen. But,
Thank you very Thank you very much for your talk. I have a question concerning on page 15 and 16, your limit. On page 15, you show that there is some background from borate neutrinos, but then if you show your limit at 40 GeV, it looks more or less completely smooth. So is there no impact on the limit calculation, or is this background not really affecting your sensitivity?
Yes, the boronate neutrinos affect your sensitivity to the extent that they overlap with a particular signal model. And so the 40 GeV, for example, a 40 GeV WIMP, there's not much overlap with where the boronate comes in. And so we can mostly, cut it out at some level spectrally, I would say. So as the WIMP mass gets lighter and it starts to overlap with the boronate, and so it cuts in there. So our limit at something like 6 or 7 GeV is significantly worse than it would be if the boronate did not exist. So I would say that the boronate affects you below 10 GeV, but above that mass, it doesn't really affect you very much.
Okay, thank you.
Then we have a question from Zhang Lai.
Yes. So thanks you for this talk and very impressive progress despite this pandemic. Very good. So I have you made the comment about this low energy electron recoil access. You said that for example, the tritium problem. I wonder what's the counteract of LZ for these unknown, untraceable amount of the tritium if it's indeed in there, instead of just constraining it. What's the counteract if you actually see something?
So, sorry, I was with you until the very end. Instead of constraining them, what
right? If you see if you see something excess there.
Say we see an excess, yeah.
Right.
What do you do?
Right.
We've been thinking about this a lot in the last 3 weeks, and I think you do what you can. so that 37 argon is maybe an easier case where there's like a much clearer time dependence. So if you have some supported leak, I mean, tritium too, I suppose, you have to start playing with things like flow rate. So if you think your background is coming from, a leak, you can play with flow rates to try to understand that, or you can look at time dependencies. If it's some supported, we've been thinking about like activation of titanium, then that leaks out into the TPC. That's something that's very, very hard to put a handle on. And so there, maybe statistically, you can start to do spectral discrimination. But at the moment, I would say we don't have a great answer, except that we're thinking about it really hard.
Okay, thanks.
I know you. What are you guys doing?
Well, we do have the distillation, so
yeah.
Anyway, it's an obvious answer. So it might not work though.
Thanks. And then we have the last question before the coffee break by Paolo Agnes.
Yeah, hi. Thank you so much. So I'm curious about the neutron tagging efficiency that you mentioned at the beginning, and I was wondering whether. So my understanding is this is the combination of the skin plus gadolinated scintillator, and does it refer to the neutrons that survives the TPC cuts?
That's a good question, and I'm not sure I know the answer off the top of my head. I think it's maybe, well, I shouldn't answer it. I just refer you maybe to the paper, but I know that if we turn off the vetoes entirely, our neutron rate would go up by something like an order of magnitude of single scattered events. But I think it's probably established over a larger number than that, but maybe I should not speak without true knowledge.
Okay, thanks.
So thank you very much, and a virtual round of applause for all the speakers for today. And we've come to the coffee break now. So we will resume in about 10 minutes at 9:30.
9:30, yes.
Yes.
So do we have all the speakers for the next session? Let me check.
Yeah, I should have. I was too interested in the talks and I didn't do my convening job. Okay. No, but I think we have the CMS talk is probably the only one that was missing.
Yeah, that one was missing, but
now it's there. Okay, everything's there.
There. Okay. Do we have the speaker as well? Maybe Xiaoyan.
Yeah, everyone is there.
Yeah, here.
Could you please, give it a try, share your screen. You want to try your camera as well?
Sure. Let me get it started. Okay, can you see my slides?
Yes.
Does it?
Yes.
Can you see this?
Yes, that's full screen. No problem. Looks good.
Can you see the second slide?
We can see the second slide, yes.
If you want to turn on your camera, but if you don't
Yeah,
want
we cannot
to,
see
no
you.
problem. Yeah,
Ah,
we see a
right.
black box. Yeah,
So,
perfect. Yeah, now we should
Very
be
good.
able
Okay.
to see both.
Great.
Good.
Cool. Okay. So, Ramin,
Can you hear me?
yes,
Mhm.
good.
Hello.
Hi. Could you try?
Yeah, let me try to share the screen.
Right.
Does it work?
Yeah. So if you can make it full screen.
No, it doesn't. It goes to full screen and then it comes back.
No, okay. So we had the same problem before. So I think
now it's working.
We cannot see the slides. We see a black
It's
screen.
black,
Right now.
yeah. So if you try to share a full desktop, this may work.
I'm sorry?
If you share your entire desktop and then switch to full screen, this may work.
Okay.
Start at 3:30. Okay, 5 minutes left.
Yes.
Okay.
Does it work?
Yeah.
It's fine now?
Yeah,
Yes.
perfect. Thanks.
Okay, wonderful. Who's
Then we have Jochen.
Jochen, yes.
I'm here. Just give me a second.
Sure.
So I see my video now.
Yes, we see you.
Let me. Where is it? Can you see my video? Am I?
Yeah.
And yes, it's not full screen.
That's fine. Does it work?
It's inside the application, so we sort of see the pages, but it's not a full screen. Either way, I think.
Is it now full screen?
More full
not
screen
yet.
than before. It's more than before.
It's 80% full screen. If it's too hard, then that's okay.
I'm just using.
Now it's doing something.
I think it's fine if we. I mean, even if we have
fine,
it like this, it's okay.
Yeah.
It's one single page and it's good. Yeah.
That's okay.
Okay, fine.
Good. Okay. Max. I'm gonna quickly grab a coffee. I'll be right back. Okay, so maybe we should get restarted. It's 3:30 now. Xiaoyue, are you online? So the next speaker is Xiaoyue Li, and her talk is on Mad Max. Please. Oh, you're already sharing. Go ahead, please. We can see your screen.
I'd like to thank the organizers for the opportunity to talk about our dielectric haloscope experiment, Mad Max. So it's dedicated to the search for axion cold dark matter around 100 micro eV. Can you also see my mouse?
Yes.
Okay, good. So as the previous speaker has mentioned, the motivation for axion searches is the so-called strong CP problem. So in the QCD Lagrangian, you have this term, which is CP violating, and you would expect the CP violating angle to be an order 1 parameter. However, from the neutron electric dipole moment measurements, we know that the theta is extremely small. This is actually weird considering the fact that theta has 2 contributions from 2 different sources. And this is the so-called strong CP problem. The Petrikhin mechanism is one of the most elegant solutions to this problem. And as a byproduct, it also predicts a light pseudo-scalar boson, namely the axion. The Petrikhin mechanism introduces a global U1 symmetry that spontaneously breaks at a very high energy scale very early on in the universe. And later, as the universe expands and cools down at around QCD phase transition, the QCD vacuum structure tilts this Mexican hat, and then this field starts to oscillate around this minimum. And as the universe expands further, the oscillation is dampened. And in the present day, it remains as a very tiny oscillation around the bottom of this potential valve, hence the small theta value. The prediction for the axion mass and abundance is no easy task, and their values critically depend on the sequence of 2 critical cosmological events, namely the Petrikhin symmetry breaking as well as inflation. So if the symmetry breaking had happened before inflation, the mass or abundance would depend on the initial alignment angle in the patch of our universe. And in the second scenario, you would have to do sort of an averaging over these initial misalignment angles. And there are lots of complications that could go in these predictions, but in any case, so these are the 2 mass ranges that most theorists agree on for these 2 scenarios. So far, most of the haloscope experiments have focused on the around 1 micro EV or up to 10 micro EV range, whereas we're more concentrated in this mass range. So unlike the WIMP dark matter, our axion dark matter is wavy in the sense that you can consider it like a classical wave. This is because, for example, for an axion mass of 100 micro EV, if we assume that it constitutes all of the local dark matter density, then you can calculate that it has a very long de Broglie wavelength, and the phase space occupancy is extremely high. So this is why we normally think of it as a classical wave. And our detection channel is the same as what the previous speaker has described, which is the axion to 2 photon coupling. This is the Lagrangian, where this is the coupling constant. It depends on a order 1 and a model dependent parameter as well. So if we put our detector inside a magnetic field, so we can effectively replace this one of the photons with a virtual photon provided by this B field. So you can convert all of the energy from the axion into a photon. So for our 100 micro EV axion, the signal that we expect would be around 25 gigahertz. And you can also write down this axion modified Maxwell equation. So only this term is the leading term in our case. So the consequence of this term is as follows. So you can see this sort of sketch. If you have this static axion, this axion field inside of a B field, it would source a static electric field. But the magnitude of this electric field is very, very small. It's something like 10 to the minus 12 volt per meter. This is even given a very strong B field. So traditionally, the way we try to detect this small signal is to couple it with a resonant cavity. So in this way, you can get the signal up to something like 10 to the minus 22 watt. And if you look at this expression for the signal power, you can see that it's proportional to the volume of the cavity, the form factor, and the Q factor of the cavity. So typically, the size of the cavity is scaled by the Compton wavelength, which means if you go to higher frequency, you typically have to reduce the size of your cavity. And also, when you do that, it's also very hard to get a very high Q factor. So this means if we were to search for higher mass axion, or therefore higher frequency, we have to think of another way. Hence the idea of the dielectric haloscope. So if you look at this static electric field, you notice that it has a dependence on the epsilon. This means that if we have a second medium in this B field, the E field will have a discontinuity at the boundary between the two medium. But the Axion-Maxwell equation still doesn't allow this discontinuity. As a consequence, you have two propagating electromagnetic waves emitted from this boundary to compensate for this discontinuity. And we can also calculate the power that carried out by this propagating wave if this part is a perfect electrical conductor. And when you do that, you can find out that the signal power is still very, very small. It's on the order of 10 to the minus 27 watt. But instead of having one interface, we can have many, many different interfaces. And if the total length of your detector is much smaller than the de Broglie wavelength, we can think of the emission coming out of each interface to be coherent with one another. And if we choose the disk thickness carefully and place them in the correct positions, we can coherently add up the emissions from these disks, and there will also be resonances between these interfaces. And we can get an enhancement relative to the case where there's only one mirror. And this enhancement is what we call the boost factor, beta squared. And if you look at this formula for this total emitted signal power, you can see that, so if we can get the boost factor up to 10 to the 4 to 10 to the 5, then this signal becomes detectable. And also it requires that the disks to be on the 1 meter squared level. And this is the basic idea of the MAPMAX experiment. And it's well suited for the detection of cold dark matter axion in the mass range of 40 to 400 micro eV. And one interesting property of the boost factor is that if you integrate over frequency under the of this curve, you find that the area stays the same, and the more disks you add, the higher the total the boost factor area becomes. So this means that we have two options for the scanning. One is a broadband scan where we sacrifice the boost factor for a broader bandwidth, or vice versa. And this plot shows you that you can actually continuously tune the boost factor beta squared frequency by changing the disk positions only without having to change the disk thickness every time. And this contour shows you that the beta squared is quite stable against some uncertainties on the disk positioning. So this means it's experimentally feasible. So far, I've told you that everything will work out theoretically, but you may have questions as to whether this will work in reality. So in the remainder of the talk, I'll go through some of the real world effects, namely some of the effects from the imperfect disks, and how we can know where the boost factor is, given that it's not something that we can measure, and how do we detect such a small signal, and some of the engineering challenges as well. So we have done a lot of simulation studies on these more realistic disks and the consequences on the boost factor. So for example, this plot shows you the boost factor, how it's affected by the different level of thickness variation on a correlation length of about 10 centimeters. So this is the case where we have 80 1 meter diameter disks, you can see that, of course, they can be adversely affected by the thickness variation. So this shows us that as long as we can maintain a disk flatness better than 5 micrometer, we can still get a reasonably good boost factor. And I should point out that these effects could also be mitigated through the measurement-based tuning that I will mention later on. And we've also studied the disk tilting effect, and the conclusion is that for this 1 meter diameter disks, it should be better than 0.1 milliradian. So this would correspond to a 100 micrometer displacement from one side of the disk to the other. So this is also within the precision of the motors. And another consequence from the non-ideal disks is that it can give us an irregular beam shape out of the boost factor. So normally we would couple this axion-induced beam with the Gaussian antenna. So if the boost factor, if the beam shape looks like this, then you would also expect a reduced efficiency with the antenna coupling. And how do we build such a large disk? So in the nominal design, the disk will be about 1 meter in diameter and 1 millimeter in thickness, and they should have relatively high dielectric constant and low dielectric loss. So far, we have studied in detail 2 candidate materials, namely lanthanum aluminate and sapphire. Unfortunately, these single crystals don't normally come in as big a size as 1 square meters, so tiling might be needed. So we have at University of Hamburg, they have developed this tiling scheme where they laser cut these lanthanum aluminate samples into hexagon tiles and align them with the camera. And here you can see this dispenser moving around and filling these gaps with a die-cast blue glue. So this is their first tiled lanthanum aluminate disc with about 30 centimeter in size. And of course, we're also investigating other possible candidate materials, and more importantly, the effects of these tiles on the electromagnetic properties of the booster are also being investigated. Next, I'm going to talk about the frequency tuning, and this is a setup that we used for these studies at MPB in Munich. So you can see here, well, actually half of the booster with 1 copper mirror and several sapphire discs, each with 20 centimeter in diameter. So we can send in a signal through this antenna and measure the reflectivity from the booster through using the VNA. So this is what the setup looks like now in the lab in reality. So the frequency tuning procedure is based on the understanding that the same interfaces that give rise to the boost factor would also determine the electromagnetic response, such as the reflectivity. So these two are very strongly correlated. Then we can use the latter to tune the former. So what it works in reality is that we make a prediction of the boost factor that we'd like to have, and then we also make a prediction for the reflection group delay, show in the blue curve, and then we iteratively move the disks in the setup until the measurement matches with the prediction. You can see that at least up to 4 disks, this works quite well, and these tiny ripples are due to the impedance mismatch of the at the antenna aperture. This is somewhat irreducible. And the benefit of this tuning procedure is that it somewhat reduces the need to only rely on a good simulation or very precise knowledge of some key booster parameters, such as the dielectric constant, which are very difficult to measure precisely in this frequency range. And also, we don't have to know the disk positions before the tuning in this case. However, this tuning procedure does has some introduce some intrinsic uncertainties on the boost factor. This is because that there exists degeneracy among the disk spacings. So for example, in the case with only 2 sapphire disks, you can clearly see a correlation between the distance between the first mirror and the first disk and the distance between the first and second disks. And the single disk repeatability gets worse when you have more disks because of this degeneracy. However, this also means that the impact on the boost factor is actually, it doesn't grow so dramatically. So as you can see that in the case with 5 disks, the uncertainty due to this tuning procedure on the boost factor, so in terms of frequency, is on the order of 1 megahertz, and it's on a percentage level for the amplitude. So I've mentioned before that our signal level is on the order of 10 to the minus 22 watt. So in order to be able to detect such a signal, so first of all, we need to have a cryogenic environment for the booster, and also we need a very low noise receiver chain. So we have built up this receiver chain in the lab in Munich, where the potential axion signal would be received first by this cryogenic low noise amplifier with a noise temperature of around 5 Kelvin. And it will go through 3 heterodyne mixing stages where the 10 to 20 gigahertz signal is mixed down to less than 50 megahertz, and then it's collected and analyzed. We have tested this receiver chain by injecting a fake axion signal at about 10 to the minus 22 watt. And here you can see the front-end mixers and amplifiers, which corresponds to the first 2 stages of the heterodyne mixing. And so the 4 samplers would collect the signal, and they have internal FPGAs that can do fast Fourier transforms, and they're connected in a daisy chain, so we can reduce the dead time. So this is the result of such a measurement, a fake axion measurement. So this shape comes from the shock noise of the amplifier, as well as the shape of this filter. And if you zoom in, you can see this tiny peak here. So this is our fake axion signal, and it's detectable within a few days of measurement time. In the future, we hope that we can further reduce the system noise temperature by swapping out the HAMP amplifier with a quantum limited traveling wave parametric amplifier, or 2PA. So we're working with collaborators at Neo Institute, where they have developed this 2PA which is made of about 2,000 squids. So their current device works at about 6 to 7 gigahertz. So you can see that they have a very broadband. It's a broadband detector with 50 dB gain, and it can operate near the quantum limit. However, there hasn't been any 2PAs that works beyond 10 gigahertz, but they're working on its development, and we hope that the testing can be started relatively soon. And in order to get down to the QCE line, so this is sort of our wish list design. So where you see this booster with 80 lanthanum aluminum discs, each with 1 square meter in area and 1 millimeter in thickness. And here you can see the focusing mirror and horn antenna. And this will also all be cooled down to 4 Kelvin temperature. And the B field will have to be on the order of 9 Tesla, and it has to have a larger than 1 square meter aperture and very high homogeneity across a 2 meter distance. And of course, this places some extreme engineering challenges, particularly on magnet. So our figure of merit is the B squared times the area, and we want it to be 100 Tesla square meter squared. And this type of magnet has never been built before, and a lot of design studies have gone into this, and eventually they came up with this dipole magnet design, and you can see the simulated B field along the cross section. So it's almost 9 Tesla and very homogeneous. And it has been decided recently that we would go through this intermediate stage where we first built the 5 smallest coils, and which would give us the same aperture, but somewhat reduced b squared times a. And we can already use this for data taking that would give us some meaningful physics result. And eventually these same coils would go into the final magnet that will give us 100 Tesla square meter scale. And this is our tentative timeline for the experiment. So the collaboration was only formed in late 2017, and we published a white paper not so long ago. And we're currently in the prototyping phase. And hopefully by the end of this phase, we'll have a prototype detector that we can operate without magnet at University of Hamburg or with magnet at CERN, where we can use this Mofogo magnet that can give us a magnetic field up to 1.6 Tesla. And in the meantime, while the prototype detector is taking data, we'll start the construction of the final detector and the magnet, and hopefully we'll be able to start data taking first with this reduced magnet, and then later with a full magnet at DAISY. Just want to say a few words about the prototype detector. We already have a CAD drawing here. You can see this small booster where we have 20 lanthanum aluminum discs with 30 centimeter in diameter. And in this instance, we'll also have a laser interferometer incorporated for the distance measurement. And one of the most high-risk components in this design is the disk positioning mechanism. And we require the motors to be able to work at 4 Kelvin, 9 Tesla with a long travel range and 6 kilogram load bearing. So basically the only option would be the PSM motors, and the development and testing of these motors and the carriage is ongoing. And we hope to use this prototype detector to search for a hidden photon or ALP around 80 micro eV. I'll leave you with the sensitivity projection for MATMAX. Here we show, and also the sensitivity for the prototype detector with 3 months of data taking. And yeah, if we can reduce the system noise temperature, and we can even get down below the DSVZ line here. So thank you for your attention, and I'll take questions.
So one of my Zooms crashed, and I don't know if Zhanglai is also having problems. Anyway, thank you very much for the talk. Let's take the questions. Sorry, minor technical problems as well. So Zhanglai, are you trying to, yeah, I don't know who is trying to ask a question there. It might be, there's a Zhanglai that might be trying to speak or ask a question.
I'm sorry, I can't hear anything.
Can you hear me as well?
At least? I can hear you.
Okay, yeah, so it might be that it's a technical problem on Zhanglai's side. So I guess let me ask a question on the experiment, and then we can move on to the next talk. So I'm wondering how you're treating the complementarity between different axion experiments. So how is the community working? Are you working together? Are you sharing technologies? Or are you sharing results? Or is there a sort of action experiment group? Or you work independently mostly from other experiments?
So if you look at this plot, you can see that there are already some exclusion regions by ADMX and the other experiments. So we're more or less looking at different frequency ranges. But recently, a lot of groups have been trying to use this quantum limited amplifier. So I think there's some synergy in there. But otherwise, I think we're working more or less independently.
Okay, thanks. Because it's such a fast growing field, I think that it's the question comes from the organizational questions come, right? So yeah, thank you. Okay, we can move to the next talk, which I believe goes into a very different mass range for the dark matter particles. And that is Raman Khurana with the search for dark matter at CMS. We can see your slides now.
Are you muted?
Yeah, Jangla, you might be.
Can you see the slides now?
Yes, now we can hear and see you. No, not see you, but hear you at least.
My camera doesn't work well.
No worries.
So I just keep sharing the slides and go on.
Yes, perfect. Thank you.
Okay, thank you. Hello, everyone. So I will be presenting the results for the dark matter searches at CMS experiment. The result I show here are basically using the full or partial data set from run 2 of LSC. That is the data collected in year 2015 to 2018, which correspond to a maximum of total LUMI of about 140 femtobarn inverse. So one of the reason, as is evident from other talks also, one of the reason to search for dark matter candidates at Collider is availability of multiple evidences from astrophysical and gravitational observations. And they also show dark matter is long-lived, electrically neutral, and does not participate with any of the interaction we know so far. The hunt for dark matter is on in various direct detection, indirect detection, and collider experiments. And the collider search complement the direct and indirect searches while searching for the favorite dark matter candidate, which is weakly interacting massive particles, commonly known as WIMP. So this is a quick look at the onion style layered CMS detector to quickly show the location of each subdetector and what it does. So right after the collision point comes the pixel detector, which is a very fine grained detector to detect the particle tracks. And then comes the strip tracker, which in combination with the pixel reconstruct the charge tracks in the presence of 4 Tesla magnetic field provided by the solenoid. And after the tracking comes the electromagnetic calorimeter to catch the shower of electrons and photons. And then comes the hadron calorimeter. And broadly speaking, at the end, we have a muon spectrometer, which is last layer of the detector in the returning magnetic field of the strength 2 Tesla. It can be clearly seen from the legend that how and where each particle deposits the energy and can be detected. So this is about the standard model particles, but for the dark matter candidates, it's completely different. So because it doesn't interact with the detector or any collider detector we know so far. So what happens is it remains undetected and it results in high missing transverse momentum in the detector. So coming to the next one. So CMS has a very rich dark sector search program. And one of the most common is to search for the invisible dark matter produced in association with one or more standard model particles. And the main focus here is on the simplified models where dark matter couples to standard model via a heavy mediator, mostly a S-channel mediator, which can have a spin 0 or spin 1. And based on the spin and parity of this heavy mediator, we can have different scenarios, basically axial vector, scalar, or pseudo-scalar mediator. And some of the parameters for this kind of models are basically spin and parity of the mediator, coupling of the quarks and the coupling of the dark matter, and then the mass of the dark matter and the mass of the mediator. So these are the main parameters which play a role in the final results. And since dark matter search program is very vast at CMS, starting from SUSY to usual MAT+X searches and then going to long-lived displaced particles, I plan to cover only a small subset of them. And I show here a brief list of the analysis which are covered here. And the full set of the list of dark matter searches, you can click the link here. So let's start with the first analysis, which is basically searching for the dark matter in Z to dilepton final state, where dark matter remains undetected. So the final state becomes Z plus MET, which is commonly dubbed as mono Z in collider experiments. So what you see in the detector is a pair of electrons or pair of muons, which is coming from the Z boson, plus an invisible energy, which is reconstructed as missing transverse momentum. So the results are interpreted in multiple theoretical frameworks. So namely dark matter, Higgs to invisible, extra dimension, and unparticle. But I consider here only the dark matter and Higgs invisible, which are more relevant for us today. So for the dark matter searches, there are two different models which are considered. The first one is a simplified dark matter model, where a heavy pseudoscalar A decays into a pair of dark matter particles. And the other one is 2HTM plus A model, which is relatively new framework, which CMS and Atlas experiments are considering now. So in this model, there is the dark matter couples to the light pseudoscalar boson, which comes as a decay product of the heavy Higgs boson of the 2HTM framework. And the major backgrounds for this analysis comes from WZ, ZZ, and non-resonant production of TT bar, TW, and WW, and then finally the trillion plus jets. So a dedicated control region for each of these backgrounds are built to control the normalization of each of these major backgrounds. So here you can quickly see the selection for the signal event and also what it does to the major backgrounds. What are the backgrounds which are detected by this particular selection? So the analysis strategy for mono C is really simple. So it uses the control region for major background and constrain the contribution of the major background in signal region by constructing a simultaneous fit of signal region as well as the control region. And to increase the final sensitivity, the analysis is performed in two different jet pins. That is when additional number of jets are 0 or 1. And then the simultaneous fit is performed on the missing transverse energy for all the interpretations, except for the 2HTMA plus A, where where it is getting a benefit from the fact that Jacobian peak can be reconstructed. So it is using the transverse mass of the dilepton and met. So here is the quick summary of the mono Z results. So on the top left, the plot shows the 95% upper limit on the mediator mass versus dark matter mass plane. So here it is considered the vector nature of the mediator, and you can see the region which is excluded by this search alone. And the bottom left shows the 90% confidence limit on the spin independent dark matter nucleon cross section as a function of the dark matter mass, and we can see that it's in a very small phase is where no other experiment is reaching just to very small phase where CMS has done something. And the next interpretation is in terms of 2HTM plus A model, where the upper limit at 95% confidence level are placed in the mass plane of light pseudoscalar and the heavier pseudoscalar, and it covers a big space phase if we talk in terms of the exclusion. And the results are also interpreted as an upper limit on the branching ratio of Higgs to invisible. So the assumption here is the standard model Higgs boson is of 125 GeV, and the observed upper limit here, which is seen, is about 29% for the branching ratio of Higgs to invisible. So next in the line is the search for the dark matter in mono Higgs final state. So the Higgs was discovered, or discovery was announced in ICHEP about 8 years ago. And after that, it's possible, I mean, once the Higgs boson candidates are enough, it is possible that we can search for dark matter in Higgs plus met final state. So here you can see different branching ratios for the Higgs to different decay modes. And CMS does this analysis in 5 final states: Higgs to BB, Higgs to gamma gamma, Higgs to tau tau, WW, and ZZ. And by performing this analysis, we try to cover almost the full space as each decay mode has its own pros and cons. For example, the Higgs to BB decay mode has a very high branching ratio, but it comes with huge background. On the other hand, Higgs to gamma gamma and Higgs to ZZ has a small branching ratio, but also a small background and a very good mass resolution, which might be very good for which has a very good discovery potential. And the results here are interpreted in terms of three models. The first one is Z prime 2HTM model, where a heavy Z prime boson decays into a pseudoscalar and a standard model Higgs boson, and then A is coupled to the dark matter. So the model predict very, very high Higgs boson boost. And the next one is the one which is commonly known as baryonic Z prime model, where heavy Z prime radiates a Higgs boson, which further decays into standard model like regime, and Z prime itself decay into a pair of dark matter particles. This model predict kind of relatively low boost compared to the Z prime 2HTM for the Higgs boson. And the last one is the 2HTM plus A model, which is similar, which is same as which we just talked about in the mono Z case. And the boost for the Higgs boson is almost similar compared to baryonic Z prime for this case. So the table here shows what are the analysis or what are the further decay modes which are considered for the mono Higgs at CMS. And the first analyses are performed for each categories, and then finally a grand combination of all these is performed. And it has been taken care that all these analyses are orthogonal to each other to avoid any duplicacy in the any duplicacy of the events in analysis. And due to high branching fraction of to Higgs to BB, the Higgs to BB has been the most sensitive and different analysis strategy has been used for medium and high boost. So for the medium boost, that is 2HDM plus A and baryonic Z prime, CA15 jets are used, which is a much wider cone jets. And for the C prime 2HDM, which is very boosted Higgs, AK8 jets are used. And here are the results for the mono Higgs analysis. So on the left, you see the 2HDM plus A model. This model is looked at only by mono H2BB analysis. So right now it covers, it already reached some of the phase space with the 2016 data alone. And the other two models, baryonic Z prime and Z prime 2HDM, all the 5 decay mode, look at them, and you can see here the exclusion curve in 1 dimension as a function of mz prime for given values of the parameter. The analysis has very good reach in excluding the phase space available. And going to the next one. So this is a slightly different one compared to what we discussed so far. The search here is for the Higgs boson, which is decaying into invisible particles. And it is done in VBF, which is shown here, and also in VH and clone-clone fusion mode. So that, sorry. So in the Higgs portal dark matter, the dark matter couples to directly to Standard model only via Higgs boson. And we know that in Standard model, the Higgs to invisible branching ratio is of the order of 0.1%, and any deviation from this might be a hint for new physics. So that's why it is really interesting to look at this particular final state for the dark matter searches. For the VBF mode, the search is basically performed in high delta eta and high mass, high digest mass, because these are the main characteristics of the VBF searches. So we try to fully exploit this property of the VBF events. So the signal events are triggered with high MAT, and the signal is extracting via a simultaneous fit of signal region and multiple control region to constrain the major backgrounds. And the major backgrounds for the major background for the analysis are G nu nu and W to L nu. The figure here shows the distribution of events in data as a function of the digest mass and how well it is modeled in the simulation. So coming to the results for this analysis. So the results here are shown for the 13 TeV for all the 3 analyses I just said, and then also for 7+8 TeV, and then the combination of 7+8 and 13 TeV. So we can see that the 95% upper limit on the Higgs invisible branching ratio is of the order of 0.19. And the results are also interpreted for the spin-independent dark matter nucleon interaction cross-section, and also compared with the other direct detection experiments. So here, both the cases when dark matter, both the scenarios for dark matters are considered when the dark matter is a fermionic and when the dark matter is a scalar. So we can see where this analysis works best in the low mass region. And here's a quick summary of the vector mediated search given the set of coupling. Basically, the coupling to the dark matter is set to 1, and the coupling to the quarks is 0.25, and coupling to lepton is 0. And we can see that a big phase space is already excluded, but there are still regions which are not yet excluded and cannot be reached with the present luminosity. But the point to be noted that it is only for these values of the coupling, and the exclusion curve here or the results here depend a lot on the coupling value chosen here. So the next in the line is again slightly different from the conventional MET plus X dark matter searches. Here we assume that the search for a particle is here we assume a new set of particles typically charged under the dark forces will allow interaction between the standard model and dark matter via loop by some kind of induced mixing. And in the present scenario, I want to discuss here the dark photon. The dark photon is the particle which mixes with the standard model with a standard photon and induces the coupling to the fermion. The strength of this coupling of this dark photon to the standard model particles and the degree of mixing is governed by the kinematic coefficient epsilon. And the analysis which covers this is the search for the dark matter in the Higgs boson decay via two photons, where one of the photon is a dark photon and it remains invisible, and the events are tagged using the forward-backward jets coming from the VBF. Here, the main interest is on the Higgs boson with 125 GeV. However, the results are extended to higher mass values also. The search is performed by simultaneous fit again using the transverse mass of the Higgs boson. And a different and very complicated trigger strategy has been used for each year. So in the 2016 VBF photon triggers are used. However, for 17 and 18 MET and photon triggers are used and then later on combined for the final results. And here you can see the signal selection for each of these cases. For the VBF trigger, for the single photon trigger, and for the MET trigger. So this is driven by there are slight differences in the selection, and it's driven by the trigger strategy of the analysis. So dedicated control region are formed for each of the major background, namely W plus jet, W gamma, Z gamma, and gluon plus jets. And finally, the signal is extracted via simultaneous fit of signal and the background. So here I quickly describe how this simultaneous fit works for this analysis. So we have a signal region divided into two bins, also the control regions, which is mass of the dijet less than 1500 GeV and more than 1500 GeV. And the first three bins in the signal region are tied to the first bin of the W plus jet and so on, following these brackets. And the control region for gamma plus jet, C gamma, and W gamma are one bin control regions as described in the table here. And the similar strategy is followed for the other case when MJJ is greater than 1500. And then a simultaneous fit is performed to extract the signal. And and here is the result for the analysis. So 95% upper limit of the production cross-section is extracted. The total line here shows the predicted signal cross-section to the 5% of the VBF Higgs boson production cross-section. And the upper limit on the branching ratio is also extracted for VBF, ZH, and the combined limit, which we see is of the order of 2.9% for Higgs going to dark photon plus normal photon. So a quick summary is we have showcased the recent selected dark matter searches from CMS, and a wide range of dark matter search analyses have been performed, but only a few of them are shown here. So personal interest, and many of them are still under progress, and stay tuned for new results. Thank you.
Thank you very much for the nice talk and for the new results. It's always nice to see what comes out at ICHEP, the new things. I see that there is one hand up, I think, from Kalpana Bora. So please ask the question.
Yes, hi. Thanks for the nice talk. I have a question about, could you go to your slide of that scalar dark matter particles? I want to have a look at that. I mean, what are the recent limits?
This one?
The scalar dark matter one.
You mean from Higgs to invisible, or? So this orange line, line is the scale. It's considering that considering the scalar nature of the dark matter candidate.
Okay. Okay. Yes, this one only.
As a function of the dark matter mass. Yeah.
Okay. So your dark matter particle here is allowed to in up to this one.
So here is going below 100 GeV, around 80 or so.
Below
so.
Below 100 GeV. Okay.
Yes.
So this below this is the allowed region, is it?
Yeah.
Below this yellow line.
Yes.
Okay. Okay. And this is the scalar can be complex, or it is real only?
I don't have answer right now for this. I can check and just post it here in the discussion session. I don't know if the scalar considered here is complex or not. I think it's not complex, but I have to double check this.
Okay. Okay. Fine. So below 100 GeV. All right. Okay. Thank you. Yeah. Thank you.
Thanks.
You're welcome.
Any other questions? Otherwise, we move on to the next talk.
Yes, so the next speaker is Jochen Scheck. He's going to talk about the search for dark matter with CREST-3. Could you share your screen, please?
Should be there. You see it?
Yes, we can hear you. You can also turn on your camera if you want.
I turned on the camera. I have no idea why it's not sharing. Sorry.
Okay.
It's on. Anyhow. Okay. Thank you very much. So I will give you a talk about the latest results from CREST-3. So I will have basically, I'm talking about two different papers. One of the result which was already published last year. So this is called a standard dark matter search with our calcium tungstate crystals. And just recently this year, we published also some tests or results using lithium aluminum oxide to test this crystal for dark matter searches. So just as a normal intro, so we all hope or think that dark matter is just a particle which solves our dark matter problem. And besides the classical WIMP paradigm, there are now more and more theoretical motivated ideas that there might be also a dark matter candidate below the classical 2 GeV region. This is why we are moving more and more towards low mass dark matter. And this is where we very strong at right at the moment. And for example, on the right, here you see this well-known core versus CAS problem, where you would expect a Caspi-like profile, but we observe a core one. And you could, for example, explain this with a self-interacting dark matter, and this would naturally lead to some light-masked dark matter. So how we're doing this, we're looking in this direct detection via elastic scattering. So a dark matter particle from the halo in our galaxy comes in via some T-channel with a mediator, exchange of a mediator, scatters to the nucleus or nuclear of our detector, and it gives some recoil energy, and we are able to detect this recoil energy, and together with the expected astrophysical numbers, the density and the velocity of the dark matter we are in, we can use it to determine the dark matter mass. As you could imagine, just from kinematics, if you look for light dark matter, you get a much lower nuclear recoil, which you can see on the lower right side. So if you look for light dark matter, this number of recoil events versus energy is much steeper. So in order to detect low mass dark matter, you have to be sensitive to very small recoil energies. And for example, you at least require sensitivity below something like 100 eV. This is the CREST collaboration. It's actually taken at the same location as the last Mad Max collaboration picture. It's before the pandemic, so this is a real collaboration meeting. So the detection principle. So the CREST is using a cryostat at the crystal operating in a cryostat, and we are reading out two channels. Calcium tungstate is a scintillating detector. So we are able to read out the light. And the key there is that the response for impeding particles is different for background and signal events. So by detecting the light and the phonon channel, which basically is a measurement of the total energy, and meaning the nuclear recoil energy, you have a possibility to distinguish between dark matter particles, signal type particles, and background type particles. The experiment, as I said, is operated at cryogenic temperatures, meaning we are running at Consenso at 15 millikelvin. And what you can see, the nuclear recoil deposits some energy, and the deposited energy is related to a temperature rise here with this, with the heat capacity, the energy, and the mass, which means if you're operating a very small crystal, this is why you're also moving to small crystals, you get a much higher temperature rise. And also you see here the heat capacity is correlated to the temperature cube. So if you're running also at a very low temperature, you get a much higher temperature rise. On the bottom right, you see a picture of the resistivity of our detector, so that we have operating a transition edge sensor right at the between the superconducting and the normal conducting phase, and we are operating right here in the middle. So if we have an impeding particle, the temperature rises, and this means we have a change in resistivity, and this is what we observe. And here you see a picture, the nuclear recoil energy. So this is basically the phonon channel, and on the y-axis, the light yield, which means the light observed, the scintillation light divided by the nuclear recoil energy. And you see here nicely the separation, what I tried to explain before, between signal and background events. The signal type events have basically a very small light yield. For example, you could have here, this is from calibration from neutrons scattering on tungsten or on oxygen. They have a very small light yield, and background events with incoming electrons or gamma have a much higher light yield. What you can see here at the very high energy above a couple of keV, you have a very wide separation between signal and background. But what you can also see, if you look for very small or small dark matter masses, these bands do overlap, and you have a significant increase of background just from overlap of these background events from E-gamma events. For this, we need to have a dedicated simulation. What we do there, we use Geon4, and we use at a higher energy, what you see here, this is a measurement of the alpha activity between the order of 4 to 7 MeV. These decay chains we can measure, and we know that these decay chains are in equilibrium. The alpha energy, for example, here between uranium and thorium, you measure, and then the thorium decays with a beta decay, and this beta decay, the energy deposited there is actually in our region of interest. So the idea is you measure the alpha activities. We know that this is in equilibrium, and by the alpha activity, we normalize the beta spectrum, which we take from simulation, what you can see here. So for example, this is a beta spectrum from the thorium to the 340 cases. So you see the different beta decays, and also here these edges. And we take this from simulation, we normalize it via the alpha activity, and then we produce basically our background model. And this is what we published also last year. So on the lower right, you see the energy, the different contributions. The red line, this is the interesting line. The red line is basically the sum from our Monte Carlo. The black is the data. You see that for a certain range. So this is normalized to energies at the MEV, then extrapolated with the simulation down to KeV. And you see we have a nice agreement here. However, at the low energy, actually in the region of interest, and especially at this very lowest energy, we have a steep rise, which with our simulation, we cannot really explain right at the moment. This is how a detector looks like. So this here, this small is the crystal. On top, you see this transition edge sensor on the detector. This kind of brownish here is the silicon on sapphire. So this is our light detector, also read out with a transition edge sensor. Everything is hold on this calcium tungstate sticks and surrounded by scintillating foil. So in order to be also sensitive to background events, and then all in a copper housing. The crystal, as I said, has something, the calcium tungstate crystal, roughly 25 grams. The signals we get out, we use an optimum filter. The optimum filter there, the idea is that you have a power spectrum. You know that there is a difference in the power spectrum between a signal type event and a background type event. By using this information, you can basically filter out more the background and have an enhanced signal. And this is what you see here on the bottom. This is an unfiltered pulse. And then you apply the optimum filter, and you see here you get roughly an increase of the signal to background ratio by a factor of 2 or 3. We use continuous data sampling and basically set then the threshold offline with our data analysis. And this is what you can see. So this is the data or the efficiency from data between 2016 and 2018. We take roughly a fifth of the data for shaping our data analysis, for make tests and getting the efficiencies and the cuts, or get the cuts, and then we achieve a data efficiency on the full data set of roughly 65%. We have of 3.64 kilogram days as the total data size, and the light gray here is the total selected, the total triggered events, and then after all the quality cuts, we reach something like 65% efficiency. And the key is here, you see this S-shaped curve. This is the threshold, and you can see that we can reach a threshold of 30 EV. So this is why we can go to very low mass dark matter. And this is the result. On the left side, you see again the same plot, data energy versus light yield. And this yellow kind of area is our signal region. So this is 50% of the oxygen recoil, what you would expect. We can nicely separate from the gamma beta events, beta gamma events. However, if you then just take the signal region and you project on the energy, you see here we have a couple of events. So the gray are all events, the red are the accepted events. And what we observe, you see here from electron capture, some nice peaks. We have a residual background, but we have an unexpected exponential rise of events below, at low energies, roughly at energies below 200 eV. We can use this, and using the setting the limit with using the astrophysical assumptions, and this is what you can see here. So this is again on the right side, just focusing or just projecting out in the region below 1 keV, and the red is really the kind of accepted events, and with this here you see roughly at something between 200 and 300 MeV, this exponential rise kicks in, and this is why the limit grows there. And with this, we get roughly a sensitivity down to 160 MeV. This is just an overview. So what I presented you now is this CREST-3 run 1, where we reached a threshold down to 30 eV. However, we observe an unexplained rise of events below 200 eV. That's a major issue and basically is limiting our sensitivity. We had a run last year with upgraded detector modules, basically to study the origin of this background. In addition, we had also a successful test using an active magnetic field compensation. There's always a magnetic field which influences the squid measurements. The data analysis is ongoing. Unfortunately, I cannot show you any results. And just last week, we started run 3 of CREST-3 with a second round of modifications. The cool down started already in March, but then we had to stop due to the corona pandemic. But now the cool down started last week, and we hope that we can run our detectors maybe mid of August with data taking. The second part of my talk, I will show you some cryogenic operation with lithium aluminum oxide crystals. Why are we doing this? Lithium is the lightest element which can be operated with this technology, which means, of course, with the lightest elements, you can also further increase the sensitivity to low mass dark matter. Around more than 90% of lithium is lithium-7. You have an unpaired number of nuclei, which means that you are sensitive to spin-dependent interactions. So this is one we want to study. Up to now, what I showed you is only spin-independent, but now we have also the possibility to have spin-dependent measurement. And then lithium-6 can undergo neutron capture and produce an alpha, which we can measure, and tritium. So with this crystal, we are also able to have an intrinsic measurement of ambient neutrons. So to further study this and to understand if this kind of crystals is able to be used, we had several tests. I show 3 of them, or all 3 what we did. So we studied, first of all, is lithium aluminum oxide working at all. So we did some measurements of the scintillating properties, the light yield, and also the quenching factors. And then actually we use another crystal with an above ground, so where we have much more background, to see if we can make really what is the sensitivity we can reach for spin-dependent dark matter operation. There we went very low in threshold and made a measurement there. And then we used one crystal with a much larger mass leading to a higher background, went underground in the CREST cryostat, test cryostat of CREST in Cansasso, first of all to verify that it's able to measure neutron detection and also to have a radio purity measurement. So this is the first 2 measurements which were done in Munich. So these crystals were done at the Leibniz Institute for Kristallzüchtung. You see these 2 different modules. Here on the left side, you see the transition N sensor. And in addition, we have an NTD. This is the crystal. It's below a silicon on sapphire detector for measuring the light. This was used for the cryogenic characterization, also measure the scintillation properties. And this module B had no light yield. We measured this, basically used this to study the spin-dependent dark matter interactions. So this is module A, surface operation. We used 2 different radioactive sources for calibration. Here you see the iron source, and here you see the neutron source. What you can see here, nearly you can nicely distinguish or measure this iron source. And on here on the lower plot, you see a very nice separation between the beta gamma band and also for the neutrons, which is, so this is the beta gamma, and here you see the neutrons, but also you are able to see the lithium capture, where you have then the alpha with an energy of around 4.78 MeV. And this is right at this line where you see here this detected energy with a light yield just between the neutron and the beta gamma band, so with the basic where the alpha quenching factor, and you can see here, yes, we can see neutrons. The second module was then actually used really to do a dark matter limit. However, there the measurement, since it is above ground, is really limited by the background rate. And again, we use the iron source for calibration. Also, we used heater pulses. Here, the small black lines are the heater pulses, and the green line, this is from the iron source. The exposure, the total exposure, but I show you here the exposure for lithium-7, which is interesting, and for aluminum. The threshold we reached is in the order of 200 EV, and the baseline resolution in the order of 40 EV. We took this to calculate the limit, and you can see here this is for the scattering neutrons and protons, and I focus here on the protons. You see here for the scattering on protons, this is the best limit for the direct spin dark matter detection. The bluish line is from Xenon 110 with using the Migdal effect, and also here this is some analysis where they made some extrapolation using cosmic rays. So yes, it's working. It's limited basically by the background, by operating at the surface. So which means if you put it lower in a shielded environment, you might further be able to further increase or decrease the limit. The last crystal, crystal C, was really operated at the Cansasso in a test facility there. It's a huge crystal, so with 400 grams, which means the threshold, if you remember the page, what I showed you before, the temperature rise is proportional to 1 over the mass. So if you have a high detector, the threshold or the energy detection data, temperature rise is much smaller. So we there couldn't go to low energies. However, we used this last crystal in order to be more sensitive to the intrinsic background. The detector here was equipped with a transition edge sensor and with an NTT basically in order to get a larger energy range for our detection. This is the result, what you can see here. So again, we use an americium beryllium source for neutron. And you can see here, this is again this neutron capture where you see the alpha and the tritium and the energy. But what you can also see from radioactive decays, alpha decays, which you can see here before be above 4, between 4 and 7 MeV, you see alpha events. And if you look at this, so the blue one is the lithium capture, the neutron capture in lithium. The red one is alpha decays. You can see that there is a clear separation, or it could be a separation between the quenching factor values, which mean, yes, it's possible to measure the ambient neutron background with this type of detectors. The intrinsic activity was also measured, so basically what you can see here, and it's roughly comparable with a commercial calcium tungstate crystal. However, if you compare it with our homegrown calcium tungstate crystal, where we take particular care on the radio purity, it's a factor of 3, roughly worse. The further plans, so we plan to upgrade our detector with 200 readout channels in order to be able to have 100 modules, which would allow us something to operate a sensitive mass of in the order of 2 kilograms. For this, we need to go also for new cryostat cabling. We designed this and we are looking for, we have prototypes. We want to further test, push our detectors. Now we have something like 30 EV. However, we should be able to go, or there's not the limit from physics would be 10 EV. So there are studies ongoing how we can further decrease our sensitivity to go to even lower dark matter masses. And of course, we continue our studies to use different material. So we, as I said, we have this lithium aluminum oxide, which allows us also to measure the neutron ambient background, but we could also use sapphire, which we know has a much better intrinsic radio purity and would also allow to measure spin-dependent interactions. I come to my summary. So I showed you a first result from the CREST-3 with something like 25 gram calcium tungstate. We reach a threshold of 30 EV. We could reach one of the best limits between 160 MeV and 1.8 GeV. This limit is limited purely by the rising background below 200 EV, which is our main focus of studies right at the moment. This is the limiting factor. And in the parallel, we did also studies on using lithium aluminum oxide crystals, which allows us to make spin-dependent measurements, but also we have an in situ measurement of the neutron flux. You can ask questions, of course, right now. Otherwise, we have a dedicated session this afternoon at 2:30 together with people from the Cosinus collaboration, which is a large overlap to our experiment. And we are there to answer your questions in more detail this afternoon. Thank you very much.
Thank you very much for this very impressive talk. We have time for questions. So maybe I'll ask one what people are thinking. So about this low energy, very low energy access, in terms of the time dependence of such a type of events, do you see structures to convince you that it's indeed some unknown background, or how do you know this is not a signal?
Well, we know we made time studies. And so there is no clear indication what pointing to a certain type of background or what it could be. So for example, like cracks in the crystal or something are not consistent with what we observe. That we are not knowing, it's of course, it looks like a signal with the exponential rise. However, I showed you a result from a single crystal. We have different crystals, and you would naively, of course, expect that the background, if it's a signal, the signal would look identical for the different crystals. And the threshold or the rise of this crystal, the rise of the background where it starts, is not consistent between the different crystals. This is somehow pointing to the fact that it's not signal-like. If it's signal-like, you would expect that it looks like identical in the different crystals, and it doesn't.
Thank you. It's very clear. Do we have other questions? Very well. So if not, then yes, there is another discussion session as Jochen pointed in his slides. So so now we come to the coffee break. Let's thank the speaker again, and we come to the coffee break, and we will reconvene at 11 o'clock, which is 13 minutes from now. So do all the speakers of the next session have tested your screen sharing capability? I think so, right? Sebastian, Javier, Stefan. The next one is Stefan.
Yeah, I tested it earlier.
Okay, cool, good.
Hello, everyone. It is now time to resume the session. Do we have the first speaker? Yes, perfect.
Yes, hi. Can you
Hello.
hear me and see me well?
Yes, thank you. So this is going to be an interesting talk about the crosstalk between heavy ion physics and dark matter. So
Yes.
let's go ahead.
Hold on, let me just see if I can get this. Okay, yeah. So hello, everybody. My name is Stefan Königsdorfer from the Technical University in Munich, and I'm here today to talk about our measurements in ALICE of the nuclear inelastic cross-section of antinuclei with ALICE and their implications for indirect dark matter searches. So, okay, 1 second, having some technical troubles. Okay. Okay, seemingly difficult to keep this here. Maybe this is better. No, this does not work. Okay, I'll just do it with my mouse then. As a brief introduction, cosmic ray antinuclei provide a unique dark matter probe. And that is because of the very low expected secondary background. So this slide, the illustration of this slide shows the two methods by which we expect antinuclei in cosmic rays can occur. The first on the left is when primary cosmic rays, mainly proton and helium, collide with the interstellar medium to produce particles, including antinuclei. And then these antinuclei travel through the rest of the galaxy all the way to us on Earth. Similarly, on the right-hand side is the alternative method from dark matter, where some dark matter models predict that dark matter annihilation reactions can produce antinuclei as well, which can then travel through the rest of the galaxy all the way to us. But in order to actually make sense of any signal that we would see here, we need to determine exactly the primary and secondary fluxes of these antinuclei. So work on this is ongoing. So here we have a plot predicting the anti-deuteron flux near Earth and various different sources as a function of kinetic energy. It also shows various experiments and their sensitivities that are ongoing in trying to determine this. The one thing that is immediately worth pointing out is that the spectrum we expect from secondaries, so from antinuclei that are produced from interactions with primary cosmic rays with the interstellar medium, is expected to peak at much larger energies than the one for dark matter. All the different dark matter models seem to peak at lower energies. And so it's expected that at lower energies, the signal from dark matter should actually exceed the signal from cosmic ray collisions by orders of magnitude. Similar things can be said about helium-3, where it's even more difficult to constrain accurately, but shows similar patterns. Which brings us to the content of this talk and what we'll cover. We'll start off with discussing what's actually needed to calculate these cosmic ray antinuclei fluxes, what the current status is of the antinuclear inelastic cross-section measurements, which goes to say how much do we actually know about how antinuclei interact with matter. We'll do a brief introduction of the ALICE experiment and go into our method for determining antinuclear inelastic cross-sections with ALICE. We'll show our measurements of the antiproton, antideuteron, antihelium-3 inelastic cross-sections and talk about their possible implications for indirect dark matter searches. So these antinuclei have a pretty long way to go between where they are produced and arriving at our detectors. They get produced somewhere in the interstellar medium. And the first variable to consider here is the injected primary cosmic ray spectrum, so mainly protons and helium-3, because those will determine how many secondary antinuclei then actually get produced, which immediately brings us then to our second variable we need to determine, which is how they actually do get produced. What is the production process like? Then once they're produced, we need to transport them all the way through the galaxy to us, during which they undergo absorption effects and acceleration and reacceleration effects. Once they get close, there's the heliosphere, where there are effects such as the solar wind shielding being the most dominant effect and at low momenta. These are also time-dependent effects, which complicate this a little more, varying with the 11-year solar cycle. And we get really, really close to the near-Earth environment. There's shielding and deflection by Earth's magnetic field. we also need to account for background production and absorption in Earth's atmosphere. So to sum up, there's really 3 steps in calculating these fluxes. First, we have propagation, which should be common for all particles and antiparticles. Then there are annihilation reactions in the interstellar medium and in Earth's atmosphere. And then there's also the production of these antinuclei in these cosmic ray collisions. And if we look at such measurements, for example, here for the AMS experiment, we see that for the antiproton-to-proton ratio, we see that for a wide range of rigidity, the dominant uncertainty actually comes from nuclear physics. So it's really important to precisely constrain the inelastic cross-sections to reduce these uncertainties. Now in this talk, we're focusing on the annihilation part of this puzzle. And I'd also like to point out the talks by Sebastian Hornung and by Chiara Pinto with Annalise, who focus more on the production side. So now we get to the current status. What do we actually know about how antinuclei interact with matter? And for antiprotons, we know a lot. This has been measured, the cross-sections have been measured on a lot of different materials and a lot of different momenta. So we know this quite well. For antideutrons, the situation already becomes less well known. In fact, we have 2 measurements at a few materials, as shown here, at 2 different energies. And the highest energies of those, however, is around 13 GeV, which means at low energies, we don't actually have a measurement previously to the Elise measurements. And for anti-helium-3, the situation is even more dire, with the inelastic cross-sections never have been measured before. So the idea here is to use the ALICE experiment to measure antinuclei inelastic cross-sections, which brings us, of course, to the ALICE experiment. ALICE experiment is a general purpose and dedicated heavy ion experiment at a Large Hadron Collider with excellent tracking and particle identification capabilities, which makes it actually the most suitable detector at the LHC for studying the physics of nuclei and antinuclei. In this analysis, we used the ITS, the inner tracking system, for tracking vertexing and a PID measurement via energy loss, the time projection chamber, or TPC, which also provides a PID and tracking, and then also the time of flight detector, or TOF, which provides a different measurement. We'll get into this in a second. I also here want to point out the TRD, the transition radiation detector. So we didn't actively use it in this analysis, but it's situated between the TPC and the TOF detectors. And the thing about the TRD is there's a lot of material budget there. And since we're studying the interaction of the antinuclei with matter, this becomes quite important. So then we use the LHC as an antimatter factory. So at LHC energies, particles and antiparticles are produced in almost equal amounts, which goes to say that the primordial antimatter to matter ratio approaches unity with increasing beam energies. And this is also shown in the plot here. In this talk, we're focusing on helium-3 and anti-helium-3 results from high multiplicity proton-proton collisions at 13 TeV, and antiproton and antideutron results from proton-lead collisions at 5.02 TeV. And once we have then our nuclei and antinuclei in almost equal amounts, we use the ALICE detector material itself as a target. And here we have at mid-rapidity, the beam pipe itself for about 0.3%. We have the inner tracking system for another 8, and then the TPC for another 4, which make up sort of the inner 3 detectors. Then there's the TRD for 25, and also the space frame, a support structure between the TPC and the TOF detectors for another 20% of the radiation length. So there's really a lot more material if we extend the analysis all the way to the TOF. And the idea is to use raw, reconstructed antiparticle to particle ratios. The way this works. So imagine we have created our nuclei and antinuclei. They should travel through the detector roughly equally, and this should be well understood, with the main difference that antinuclei can undergo annihilation reactions and therefore be absorbed. Therefore, we should see in the data set less antinuclei than nuclei. And this can then actually be quantified. So what we do is, we don't actually correct here for detector efficiency absorption from material, because this is exactly what we're trying to study. We do correct for secondary particles and antiparticles from weak decays and spallation processes. And then we measure the inelastic cross-sections by comparing these antiparticle to particle ratios with detailed Monte Carlo simulations. Before we get into that, let's quickly touch on the particle identification we use, we use the TPC and TOF detectors mainly, which allows us to select these particles at a very high purity. The TPC gives an energy loss measurement in gas, and we can see from the performance plot here that the lines for antinuclei at low momenta are actually very well separated from other particle species. It's only at higher momenta that we then need additional information when they start mixing, and this is where the TOF detector comes in. So the TOF beta, together with the momentum measurement we get from tracking, actually allows us to do a measurement of the mass, which we can then fit in order to get a yield for the particles. And between these things, we then can get a momentum range for our analysis, where we have for antiprotons between 0.3 and 4 GeV, with everything above 0.7 requiring information from the TOF detector. For antideutrons between 0.5 and 4, with everything above 0.9 requiring information from the TOF detector. And for antihelium-3 between 0.5 and 4, with everything above 1 requiring information from the TOF detector. Also keep in mind, these axis scales are actually P over Z. So for antihelium-3, this would change then, and the actual momentum scale would be between 1 and 8. Which now brings us to our first results. So here we have the raw primary antiproton to proton ratio. We immediately see that this is below unity at pretty much the entire range, which means we have a higher loss of antiprotons in the detector material than of protons, as expected. We also see that there's this step here at 0.7 GeV. And this is due to requiring here the TOF detector, which means, as we discussed, that the particles have to go all the way through the TRD and the space frame as well, and have a lot more material budget to get through. This means that the difference in the interaction with the material is much more pronounced in this region. And then we take this and we compare it to the Monte Carlo simulation, which are detailed simulations of the Alice detector performance and of the propagation of particles and antiparticles using GeAnt4. And we see that this actually agrees quite well. But we want to make the measurement, and the way we do this is we then vary the inelastic cross-section of the antiprotons in GeAnt4 up and down until the antiproton to proton ratio is equal to the 1 and 2 sigma limits of the experimental ratio. And these are our measurements of the antiproton cross-section. The sigma in this case refers to the quadratic sum of the statistical and systematic uncertainties, as well as other uncertainties such as the uncertainty on the inelastic proton cross-section and the elastic cross-sections. And we see here that the agreement is already quite good. We'll go into this again in a second, but this is important because this is an important check. As we saw earlier, the antiproton cross-section is well known, and this shows that the procedure we use to measure this is correct. So how correct it is, we can see now here. We have here now on the plot on the right, the inelastic antiproton cross-section on the average Alice material up until the TPC. And we see that it is within 1 sigma of the GeAnt4 parameterization. The agreement is good. And then again, in the large momentum region on the average Alice detector material up until the TOF, we see that the agreement is very good. This means that the analysis procedure works, which allows us to then move on to heavier antinuclei, such as antideutrons. And here immediately we see at in the low momentum region, we see a steeper rise than expected, which is exciting. And then we see pretty good agreement at the large momentum region. Now, these are exciting results here, and these are actually the very first low energy measurements of the inelastic antideutron cross-sections at any material. And the paper showing these results and the antiproton results is newly in the archive, so you can go check it out there as well. This brings us then to the anti-helium-3 inelastic cross-section. And this is really exciting because at low momentum, the discrepancy between what we measure and the default parameterization is actually huge. The cross-sections we measure here are almost an order of magnitude higher than the default parameterization in GeAnt4, which suggests there's some physics going on here that we don't yet quite fully understand, which is exciting. At a high momenta, so anything above about 1.5 GeV, the cross-sections start to agree with the parameterizations very well. And for this high momentum region, there are also already ongoing in Alice other analyses which can constrain the uncertainties here higher and also extend this to higher momenta up until possibly 12 GeV. So these measurements here are actually the very first measurements of the inelastic anti-helium-free cross-section on any material. So this is very exciting. But before we finish off, let's talk about the effect these measurements have on antinuclei in cosmic rays. So the first thing to understand here is that particles tend to get reshuffled to low momenta, or at least can. So when we have a higher cross sections, low momentum that is below the peak, and remove some of the particles there, the few particles that get reshuffled from the peak towards this will actually make up for this. So the effect is less, which goes to say that the flux is most sensitive to the cross sections at the peak of the spectrum. Now, if we want to investigate this further, we can plug this into a simulation where we take here the production cross sections for antineutron in cosmic ray collisions. This is work by Philip von Dettigem, which is also on his new paper on the archive here. And we take this, we plug this into a simulation where we have primary cosmic rays and we propagate them through the galaxy, and we get something like this. And this is some work of Laura Scheck-Schnitte from the TUM group here, also a member of ALICE. And we see here the flux, the antineutron flux, as a function of the kinetic energy, in blue for the local interstellar flux, so outside of our solar system, and in green, what happens after solar modulation. And we have the solid lines here, which are using the default parameterizations of the antineutron cross sections. And we have the bands, which use our measurements. And we see that for the local interstellar flux, this makes a little bit of a difference at low momentum. But after solar modulation, they're actually compatible with the initial results. We can't really differentiate much between them, which means that the effect that these measurements have on the secondary spectrum seems to be quite small. But the dark matter peak is expected at low momenta. So if we call to mind this image we had earlier with the different fluxes, and we look at where our measurement is, we see that, yes, the secondary peak is above this, or within the region of where the measurement agrees quite well with the parameterization beforehand. But at low momenta, this is where the dark matter spectrum speaks, we see an excess in the cross-section, a higher cross-section than expected. Now, what this could mean is that this would reduce the dark matter signal more than it would reduce the background from secondaries, and therefore reduce the signal to background ratio for a dark matter signal in cosmic ray antinuclei spectra. This also means that potentially lower antinuclei signals that would be observed would be compatible with dark matter models. So to sum up what we saw here, I presented today the analysis of raw reconstructed antiproton to proton, antineutron to deuteron, and antihelium to helium-free ratios, and the measurements on the antiproton, antineutron, antihelium-free cross-sections based on these ratios by comparing them to detailed ALICE Monte Carlo simulations using GEON4. We showed the first low energy measurement of the antineutron inelastic cross-sections on the average ALICE detector material, a paper for which is currently in the archive. We showed the first measurement at any momentum of the helium-free, anti-helium-free inelastic cross-section, where we see a drastic difference to GEON4 for low momentum. The paper for this is in preparation. And for the work that is currently in progress, we are investigating the influence of these results on expected antinuclei cosmic ray fluxes, and we're extending the analysis to other antinuclei such as antitriton and antihelium-free, both of which are exciting prospects. Thank you very much for your attention.
Thank you very much for the very interesting talk. And are there any questions here? If not, I will ask one. So you say that it might not be the case that this is making a huge difference in the anti-deuteron flux due to the results you had in slide 16. But on the other hand, one never knows what can happen in the future. So are you in contact with the the community that has this kind of simulations, both the cosmic ray and for the I'm thinking about also the indirect detection community background, to make sure that these are included in those simulations of the backgrounds. These measurements are included.
Right. So first of all, I just want to point out that yes, the effect is small only on the expected spectrum for the secondaries. For dark matter, the effect is expected to be quite larger. And yeah, we are actually here with Philip von Dettingen, who provided us with these. We are in contact and trying to simulate this as accurately as possible and try to investigate this.
But for example, in the simulation, now I don't remember exactly the name of the simulation program. Do they have a tune that includes your measurements, for example?
I mean, there's what's used here is Galprop for these things, for the simulation of propagating this through.
But even I was thinking Corsica even, or like the cosmic ray community would benefit from this kind of measurements, I think.
Definitely, and this is something we're looking into and trying to do as best as possible. Yeah.
Okay, thank you very much. So I'm very excited about this kind of crosstalk. We have time for another question if anyone else has something to ask.
Katerina, somehow I couldn't raise my hand, but maybe I'll ask.
Oh yeah, because you're the host. Yes, you can't.
So, could you explain that? So the statement that the dark matter falls into a lower kinematic region, isn't that a mass-dependent statement? What if the dark matter is really heavy and then they have a lot of energy to annihilate? And do you actually change the region of the interest?
So in terms of predicting the actual dark matter spectrum, I'm not a complete expert, but from my understanding here, yes, the shape of the spectrum and particularly where the peak is affected by the dark matter mass. This can also be seen in one of the very earlier slides, if I can go back. Here towards the start. When we look here, we see that for the anti-helium free flux, we have different dark matter models, and with different masses, different peaks of where the spectrum are expected. So yes, it is true that this is dependent on the mass of the dark matter. However, in general, the way it is considered is that at low energies, it is still supposed to be higher thought to be higher than the secondary spectrum from cosmic rays.
Thank you.
So thank you again, and I think we can now move to the next talk.
Thank you very much.
Okay, so next speaker is also a very similar topic, this Alice detector. Sebastian, are you ready? Understanding the background in dark matter search by studying anti-nuclear synthesis in the laboratory. We can see you, yes. Good, please go ahead.
Okay. Thank you for giving me the opportunity to have this talk. And I will give you a summary of how studying the anti-nuclear synthesis in the laboratory with Alice helps to understand the background in dark matter searches. And in this case, it's again about the dark matter searches, the indirect dark matter searches via the anti-nuclear flux. And as already discussed in the last presentation, there's on the one hand, the possibility to produce anti-nuclei from decays or annihilations of dark matter particles in space, which then propagate through space to the Earth and can be measured there. And on the other hand, there's some background expected from the interaction of cosmic rays with the interstellar medium. In this case, the cosmic rays are mostly protons and helium-free, and the interstellar medium is also expected, or is also made up of protons and helium-free mostly. And as already discussed in the last talk already, we have seen for the dark matter signal, we expect a peak more towards the low kinetic energies, which is then above at low energies above some much smaller background But depending on the method you use to estimate this background, actually the expected background is quite different, as you can see in the left plot, where we have one expectation from Kefir-Blum et al. And one from Pulin et al. And they are quite different. So it's important to understand the production mechanism of light antinuclei in proton-proton and proton-nucleus collisions to constrain this background and to understand how much background we really expect. And for this, Alice can serve with interesting measurements, since we see a significant amount of antinuclei being produced in proton-proton and proton-lead collisions at the LHC. But at the moment, I have also to say that the production mechanism itself is not really completely understood, since the binding energy of these nuclei is only a few MeV, and the temperature of the medium produced, we know from other measurements that it's up to 2 orders of magnitude larger than these objects. So the question is, how do they survive in this medium, or at which stage of the evolution of the medium they are produced, and how can they be emitted from such a hot medium? And for this, to investigate this, usually 2 types of phenomenological models are used, since it also takes place at an energy scale where no perturbative quantum chromodynamic calculations can be used. And therefore we rely on either the statistical hadronization model approach or the coalescence model approach to describe the expected yield of light antinuclei. And I will quickly summarize the idea of both these models. On the one hand, there's the statistical hadronization model, which describes the emission of the hadrons, so not only light nuclei, but also other hadrons, coming from a medium in statistical equilibrium, and their relative abundances are fixed at the chemical freeze-out. So at the moment when the inelastic collisions between the constituents of the mediums cease, and the abundances, relative abundances, are fixed from this moment on. And in this model, the total production yield of the particles are expected to be proportional to having an exponential degrees, having as an argument the mass divided by the chemical freeze-out temperature. And therefore, light nuclei, since they are heavy compared to pions and kaons, are expected to show a strong dependence on the chemical freeze-out temperature. And indeed, when you look at the results in lead collisions, you can see that the statistical hadronization model using the grand canonical ensemble description is really able to describe the yields of pions, kaons, and protons, and going down even to light heavy particles like light nuclei and even hypernuclei extremely well over many orders of magnitude. But here I'm not focusing on the lead results, and if you are interested in hear more about it, you can go back to the talk by Chiara Pinto. But since here I'm focusing on proton-proton and proton-lead collisions, it's important to mention that for the statistical hadronization model, in these collision systems, the local conservation of the quantum numbers like strangeness number and baryon number has to be taken into account, and therefore you have to go to the canonical ensemble description. In the context of cosmic rays, usually more the coalescence approach is used, for example, to estimate the background, which I will show later. And in this model, the nuclei are expected to be produced at the kinetic freeze-out, so at the moment when also the elastic collisions between the constituencies from baryons, so protons and neutrons, or in case of hypernuclei, hyperons, which are close by in phase space at this moment. And the key parameter in this theory is the coalescence parameter, which links the invariant yield of the nuclei to the product of the invariant yields of its constituents. And at the LHC, we use the proton spectrum invariant yield as a proxy for the neutron one. So, and this has to be taken at the momentum where the momentum of the proton is actually the momentum of the nuclei divided by A. And the coalescence parameter is then linked to the production probability. And in the context of cosmic ray background estimates, usually 2 types of coalescence models are used. one which I call here the analytic coalescence model, where from the data, the coalescence momentum P0 is extracted, and then nucleons are expected to coalesce and build up nuclei if they are close, if their momenta are within a sphere of a radius of this coalescence momentum. And in this simple approach, it's maybe a little bit oversimplistic since there's no correlations or spin alignments taken into account, and therefore, for example, in the recent publication by Skula et al., they use a Monte Carlo hadronic event generator and produce the protons and neutrons, and taking also their correlations into account to some extent. And after some point, they start a coalescence afterburner, which checks the coalescence conditions and produce the nuclei at this stage. And then also in this paper, the coalescence momentum was the dependence of the coalescence momentum on the kinetic energy was taken into account. Another possibility is what I call here advanced coalescence, which takes, for the calculation of the coalescence parameter, takes the size of the emission region into account and the size of the nucleus. And with this, as you can see in the left side plot, we expect the dependence of the coalescence parameter on this emission region rate of the radius of the emission region, and a scaling with this. And this allows them to use nucleus and proton-nucleus data to constrain the coalescence parameter in proton-proton collisions, in addition to measurements in proton-proton collisions. And in this formalism, in principle, the coalescence parameter can be calculated without any free parameter using Wigner formalism, so taking the wave functions of the nucleons and the nuclei into account and looking at the overlap of this. And now the question is, how can the Alice detector add to this? First of all, for this one has to say, the Alice detector is a general purpose detector optimized for heavy ions, but thanks to its extremely excellent tracking and particle identification capabilities and the low material budgets, it's actually the best suited detector for anti-nuclear studies at the LHC. And in our analysis, we usually use the V0 detector to estimate the multiplicity produced in the event, so the number of particles, in this case, observed and detector, which is linked to the size of the emission region. And we use the inner tracking system for tracking and vertexing. And in this case, if we look at nuclei and not at anti-nuclei, to separate secondary nuclei from spallation reaction and remove this contribution. The particle identification is usually done based on the time projection chamber, which can also provide tracking information. And it provides the particle identification via the specific energy loss. And as you can see, and have already seen in the last talk, it's already having an excellent separation at low momenta, and in addition for particles with a charge number set equals to, like in this plot here, for helium-3. For other like nuclei like triton and helium-3, we have to take into account additional detector information, where we usually use the time of flight detector, which provides particle identification information via the velocity measurement, which can then, together with the momentum, can be translated into the mass of the particle. And by looking at the mass square distribution compared to the expected signal, we can fit the signal in background and statistically subtract the background to get the correct yield. And afterwards, we correct. In the case of nuclei, we correct for the secondary nuclei from spallation and from weak decays in the case of particle and antiparticle, and correct for efficiency, and we come to our results on the yields. And with this, I will already jump to showing the results by Alice, and I will start with the neutron spectrum in proton-lead collision at a center of mass energy of 8.6 teraelectron volts, where we were able to measure the yields in 4 different multiplicity regions plus multiplicity integrated sample. And here, since we do not measure in full transverse momentum range, we have to extrapolate to the unmeasured region to get the total production yield, which we do by fitting with a function, in this case with a Levi-Thales function, to get the expected yield outside the measured region. In addition, since at the LHC, antinuclei and nuclei are produced in equal amounts at these energies, we can improve the statistical precision by combining in this case, the anti-deuteron and deuteron spectrum together. We have also results in proton-proton collisions where we could even measure for 10 different multiplicity, charge particle multiplicity intervals. And here, again, the extrapolation is done using the Levi-Thales function. And all these measurements, together with the proton and anti-proton measurements in the corresponding collision systems, then allow to calculate the coalescence parameter, which is shown here on the left side as a function of the charge particle multiplicity density at mid rapidity, which is, as I already said, linked to the radius of the emission source, emission region. And you can see that there's a smooth evolution with the multiplicity, which is actually compatible with the coalescence calculation shown here in black and in the red dashed line. And these calculations take the radius of the emission source region and the size of the nucleus into account. And the data also shows the expected dependence on the radius of the emission region as expected from theory. In addition, we have also results on helium-3. Here I report the results in proton-lead collisions at 5 teraelectron volts, where we were able also to measure in 4 different multiplicity intervals. And the extrapolation in this case was done with an MT exponential function. And again, the trick was used that we used the antinuclei and nuclei spectrum combined to improve the statistical precision of our measurements. And lately, we have also the first preliminary results for helium-3 in proton-proton collisions at 13 teraelectron volts, where we have for the moment 2 multiplicity classes released. And here, again, the Levi-Thales function is used to do the extrapolation. And again, the trick is used to use the helium and anti-helium yield combined to improve the statistics. And here you can see in the lower plot also the check we always do. We compare the fully corrected yields and see if they are compatible with uncertainties, which is true in all the analysis we do. And with this, we can also, in this case, calculate the coalescence parameter V3 as a function of charge particle multiplicity again. And here we also see a continuous evolution with the charge particle multiplicity, which is again compatible with the coalescence calculations and indicating that this expected scaling with the radius of the emission region is also visible in data. And in addition, there's also a comparison to the statistical heterogenization model calculations, which I don't want to go into detail here, since it's not really relevant very much for the understanding the background dark matter searches. And with this, I want to already come to the question now: how do these measurements can be applied in understanding the background in dark matter searches, and what do we learn from these measurements and how they are used? And for this, I again take the publication by Skula et al. As a reference here, where they use the EPOT LHC Monte Carlo generator and then put a coalescence afterburner stage afterwards. And the coalescence momentum was taken from data. And then they produce predictions, for example, here for proton-proton collisions at 13 teraelectron volts, to compare their prediction to the measured spectrum by Alice and also by other collision systems they looked in, and they are in agreement. In addition, they also take the helium-3 and the triton results from Alice at this stage only from 7 teraelectron volts, and we hope that using the new results in 13 teraelectron volts, which have also smaller uncertainties, might help then to improve their prediction and to shrink the uncertainty on their results. And this then can be used to calculate the expected top of the atmosphere flux for different particles. Here in violet, the antiprotons are shown, which are then compared to the AMS result. And in addition, we have the results for I report their result for the anti-helium-3 and anti-deuteron, where with the new approach they use in taking the newest Alice data, except for the helium-3 and triton at 13 teraelectron volts from proton-proton collisions into account, they predict a slightly lower flux compared to the calculations from Pullin and Korsmeyer. And for helium-4, they actually expect slightly higher, I would say, but still compatible with the Pullin-1. But this is an example how the Alice measurements help to constrain and to learn about the expected background. And with with upcoming measurements, we hope that we have more, or can put good. We've seen that we, and in the Alice collaboration, can measure the production of light antinuclei in different collision systems at different energies, and that by measuring these and the proton yields, we can calculate the coalescence parameter and look at it as a function of the charge particle multiplicity, which is linked to the radius of the emission source, and which shows a smooth transition from small to large systems, indicating that the expected dependence from theory is correct, and which helps them to improve the calculations using this advanced coalescence approach, and that the anti-deuteron and anti-helium-3 results are an important input to constrain and to validate the methods used to predict the expected background in dark matter searches via nuclei, and in future data campaigns, which will allow us to get more precise and more differential results for anti-deuterons and anti-helium-3, and also first results on anti-helium-4, for example, in proton-proton and proton-lead collisions. We hope to give even more inputs to this and to help to improve the background estimate even further. And with this, I want to thank you for your attention.
Thank you very much for this very nice talk. Very interesting. So, and also, thank you for keeping us on time. So we have time for a few questions. So maybe I'll ask one. So in terms of the future measurement, the previous speaker also mentioned that this inelastic cross section is getting measured, and you get this production also being measured. So in terms of is that we need to add more anti-nuclears in this program, or it's mostly the kinematic coverage? What's the main improvement in the future that you can see in order to actually make better and better prediction, for example, for AMS and other cosmic ray experiments?
Okay, so I think for this, there are two parts which I want to go to. For example, if you look at the predictions I just reported from this paper, here actually there's an input from helium-4 in proton-proton collisions directly would help to really constrain also more the helium-4 results here, because at the moment they are constrained by the fact that we know from or we get the coalescence parameter from proton and helium and helium-3 and deuteron, and just it would be important to check and to measure it also for helium-4 to make sure that this is accurately described. On the other hand, if we take this approach, which, for example, Kevin Bloom uses, where we directly use the coalescence parameter to predict, but we get it looking at the dependence on the system size, that's important to look at this for small for different emission source sizes to really learn if the predicted or expected behavior is really reproduced in data, or the theory can really describe what we see in data there. And so I think, to cut it short, one of the interesting and important inputs will really be measurements of anti-helium-4, but also refining the measurements of the other nuclei will help.
Great. Thank you. Do we have other questions? Let me see if there are hands up. If not, thank you very much for this talk. Let's move on to the next one, last one. Thank you.
Thank you. So we go back to Axios now for the last talk. And the talk is by Javier Galanlacara for the YAXO and baby YAXO experiments. We can see your conclusion slide at the moment. Perfect.
Okay, sorry.
Yeah.
Was
yes, if you can make it full screen as before, it worked. So, yeah, great.
Okay,
thank you.
Can see the full screen now.
Yeah, we can.
Okay, so I will start thanking the organizer for giving me the opportunity in the name of the YAXO collaboration to present the updates on the action search with baby YAXO in view of YAXO. So, first I will start talking about the action search motivation. And as many of you know, the action is the most elegant solution to the strong CP problem of the standard model. There are many astrophysical hints for actions and action-like particles, like the universe transparency to the ultra-high energy gammas, the anomalous cooling of white dwarfs, and the hints for helium-burning stars. There's also some phenomenology as solar corona and flares that we do not understand very well, and new physics could contribute to better understanding this phenomenology. And on top of that, actions are a potential candidate to dark matter without being an ad hoc solution to this problem. Still, there is little experimental effort when we compare to WIMPs. There are relevant action parameter space at reach for the new generation experiments, and action-like particles are predicted by many extensions of the standard model. So the action is a very attractive particle from a theoretical perspective because it addresses problems in particle physics, astrophysics, and cosmology at once. The action is also very interesting from the experimental point of view because it's a particle that interacts with light, and there are many ideas leading to different detection techniques, and we can distinguish, we can classify experimental searches for actions for the action-photon coupling that in 3 categories. is action haloscopes, which are looking for action dark matter. We can distinguish also the laser experiments, which are looking for purely laboratory action produce actions, and action helioscopes, which is the main topic of this talk. To distinguish the different types of experiments for actions, action haloscopes are highly dependent on the model, since they require that dominant contribution of the dark matter is made with actions. The laser experiments are the lowest model dependent, since everything is cooked in the laboratory and you produce the actions and detect them at the same place. And the helioscope experiments, which have a bit lower model dependence, since we are looking for actions which are produced in the sun. And in principle, if actions exist, there is no reason they should not be produced in the sun. So those this is an advantage for helioscope technique that does not require actions to be a dominant component of dark matter. So what's an action helioscope? The idea of the action helioscope was first proposed by Pierre Sikivi already in 1983. And the idea is that photons are produced on the core of the sun at the kiloelectron-volt energy range in the dense stellar plasma. So there are, depending on the model of the action and the different structures of the sun, the actions are producing a range or the other, so different models, but they are all at the keV range, and they will escape the sun without problem due to the very low interacting processes of actions with ordinary matter. So they would travel to magnetic field, and then we use the inverse Primakov process in order to convert the action back to a photon with an intense magnetic field. And then we use X-ray detectors that detect the conversion of this action to photon. The idea was refined later on by Karl van Bieber and Raffelt by using a gas buffer to restore coherence over a longer magnetic field. That it leads to the second phase of action helioscopes, in which we recover coherence for higher action masses, and we can scan higher regions of the mass parameter space for the action mass. Here we have the different action helioscope generations. Today we are living in the third helioscope generation. This is first generation helioscope took place at Brookhaven. And as a curiosity fact, this helioscope was not moving, was not tracking, was not capable to track the sun, and it was just standing on the lab, and the taking was at the time the sun was aligned with the magnetic field, which was a few minutes a day. So we have a second generation helioscope, the Tokyo telescope, that you can see here in this picture. And the third generation helioscope, the third action solar telescope, which is the most sensitive action helioscope to date. It has provided the best action to photon coupling over a broad action mass range at the level of below 10 to the minus 10 gigaelectron volts. Here you see the exclusion plot provided by the Sun Action Solar Telescope, which corresponds to the vacuum phase and the gas phase, in which gas, the magnetic field is filled with buffer gas that allows to enhance the sensitivity to the action photon coupling for the higher action mass values. So JAXO is a fourth generation action helioscope. Already in 2011, there was some studies that point to the great potential to enhance action photon coupling by building a dedicated helioscope. And we found that we could improve the figure of merit of cast by a factor of 10,000 to 20,000. And how is that? Is the sensitivity to the action photon coupling? It depends on these parameters that you can see here. So the main part is the magnetic field that we can achieve. This is strongly limited by the technological developments of the field in magnet development. But we can increase a lot on the magnet aperture, as this is one of the big differences in the JAXO magnet, that we can increase the size of the magnet. Also, the time exposure of cast was a bit limited because it was 3 hours per day of tracking capability, while JAXO will be built in order to be able to track the sun for most of the day. The background of the detectors is also a big improvement on the reduction of background in order to be able to distinguish between a signal and action signal and the background of the detectors, natural background of the detectors. And then the optics, which are already very optimized for searching searching actions in the X-ray range, but of course, increasing efficiency to the lower energy range is something we are looking for in order to access models that are in the lower energy range for the action electron coupling. So this is very relevant depending on the model of actions we are looking at. So in 2014, this the JAXO conceptual design publication, in which we state that JAXO will be a large toroidal 8-coil magnet of 20 meters. Each bore will be 60 centimeters in diameter, and we will have 8 X-ray telescopes and 8 detection systems, including a rotating platform with services, and we will be able to reach 10,000 times the sensitivity of a signal to noise ratio of cast, and this was published in this reference here. In 2017, there was also publication of the JAXO Pathfinder, that is the JAXO technologies that are under R&D have been used in the data taking of CERN Action Solar Telescope in order to test the feasibility of the upgrades in the JAXO magnet. So the JAXO Pathfinder supports the testing new systems and R&D for JAXO, and using a small X-ray optics that were purposely fabricated for this test bed, and also test the new micro mega slow background detectors, which we learned a lot of lessons from the different R&D activities for better shielding, radio purity, and compactness of the detector. And the JAXO Pathfinder was taking data in CAS in 2014, 2015, providing the best limits for solar action searches that we see in this exclusion plot as the red line. The results were published in Nature, and then the collaboration, the JAXO collaboration, was officially born at that time in 2017. This is last collaboration meeting we had at CERN in March this year, just before lockdown due to the coronavirus. There are more than 20 institutions from all the size of the world. And the main goal of the collaboration is to build Baby JAXO. Baby JAXO is an intermediate experimental stage before JAXO, and will allow us to validate all the steps towards the construction of a helioscope from scratch. And the conceptual design was finished and presented to DESI in October 2018. And we will have 2 boards with dimensions similar to the final JAXO boards in terms of aperture. And these are the different parameters of the magnetic field, the size of the magnet, and the length. And this will allow us to increase the signal-to-noise ratio by a factor of 100 in terms of the most important parameters for the helioscope. The project has been supported through an ERC grant by Igor Irastorza to support these developments, and the CPRC endorsed Baby JAXO in May 2019. So JAXO will probe large parts of the QCD action model space, the yellow band we observed in this exclusion plot, and will cover a few interesting hints for actions or action-like particles, like the ALP miracle, solving both dark matter and inflation scenarios, other models solving the problem with the stellar cooling anomalies that will require a coupling to action electron, and other models, action-like particle models, which are of interest. JAXO will cover a wide range of the parameter space in all the action mass range. So, what's the status of the project? The project formal Baby JAXO proposal was proposed to DESI last year. The site for Baby JAXO has been chosen at one of the underground HERA halls at DESI, and the construction costs have been mostly secured. So the most critical point is passed. There are many, this is the ERC, but there are also other fundings coming from other funding institutions at different countries, from France, Germany, Spain, etc. And DESI has fully committed with 3 million euros to host the experiment. The CERN is involved in magnet design and construction, and there are very important in-kind contributions like a superconducting cable from INR or the platform from DESI, which is a Cherenkov telescope array mount. And the construction phase has just started and expected commissioning by 2023. This is the project tentative timeline. The design, construction, and commissioning has already started and is supposed to finish in 2023. And the data taking will start in 2024 with the vacuum phase. And then in 2026, we'll upgrade to the gas phase to cover the higher action mass region, and then other physics. So in parallel, we want to plan for the construction, design, and the construction of full JAXO, and this is the planning what we expect to work on the full JAXO. So the different components of the Baby JAXO magnet design, we have a common coil configuration chosen with a minimal construction risk with the existing infrastructure. I must emphasize that we have much larger aperture magnet compared to cast, and the magnet profile is not uniform. as it was forecast, since it was a magnet from accelerator physics. But this is not a strong requirement for action searches. Here we see a design of the magnet that is moving towards the construction design. For the Baby JAXO optics, Baby JAXO will use one custom JAXO optic, multi-layered coat, segmented glass Volter 1 that will be built, and one existing flight space XMM telescope from the ESA. There is a minimal risk to the project. On one hand, we have the XMM optics with the specifications very close to the JAXO optics design. And on the other, we gain the experience on the production of segmented glass optics for the future JAXO. Those are the micromegas detectors. The micromegas is a TPC-based detector. We have some thin windows in order to allow the X-ray transparency and be able to observe all the energy spectrum from actions. And they are built from radio-pure materials. There are other detection technologies, interesting detection technologies, in order to have diversity in the experiment and to cover the 8 lines of detection that the full JAXO will have, and to exploit the different capabilities of each detector, like low energy threshold, good energy resolution, and of course low background detection. So this is the place where Baby JAXO will be installed, and this is the Cherenkov telescope array that will be reused for Baby JAXO, and that is already being installed at the DESI facilities, and will allow to scan the sun for 18 hours per day. This is some drawings of the mechanical design for the detectors with the shielding and active VTO. There is a strong low background program, R&D program, to study the different components to the background. There are many years of expertise developed at the University of Zaragoza to combine active and passive shielding. Here you see the surface and underground studies of a detector background. And here you see the history plot with the different improvements on the background level of the detectors. This is the underground level we achieved in Canfranc Underground Laboratory. And there was a recent proposal to install a research facility for Baby JAXO at the Canfranc Underground Laboratory to assess the background of different detector technologies in similar conditions. So there are different setups to understand the background nature and characterize the VTO's efficiency and assess the achievable background levels. One of the main worries achieving a good background level for our detectors is the neutron radiation, because Monte Carlo studies has shown that muon-induced background is strongly reduced by using standard VTOs. However, we need to define new strategies to identify neutrons. So we have seen already in the data of CAST how VTOs are reducing background considerably by tagging muon events. And for Baby JAXO, we will use a completely new design with full 4-pi coverage and improving from an analog design respect to CAST. So I will come to my conclusions. Helioscopes can search for actions and action-like particles from the sun over a wide mass range. JAXO and Baby JAXO simultaneously sensitive to QCD actions, addressing the dark matter problem and proving astrophysical hints. Baby JAXO, it's already envisioned to reach a few 10 to the minus 11 electron volts in the action photon coupling. And JAXO and JAXO Plus will reach a few 10 to the minus 12 giga-electron volts in action photon coupling, which is 1 order of magnitude improvement over the present results. And there is a diverse physics reach like QCD actions, ALPS, astrophysical hints, dark radiation, and dark energy. So thanks for your attention.
Thank you very much for the interesting and promising talk. Something that a lot of people are looking forward to. Are there any questions for this talk? I don't see any, so maybe I will ask one. So it was very interesting to see a lot of the hardware and the developments of the instrument itself. But can you tell us a bit more, or at least me, because I'm not necessarily from this kind of experiments, how your data analysis takes place? Like, what is the kind of computing pipeline, anything that you use afterwards?
Well, the data analysis is quite simple, but it's also challenging. We use the topology, the event topology in the detectors. Actually, we use Micromega's TPC as a baseline for Baby Jackson. There we can distinguish different types of radiation, like cosmic muons and multi-cluster events, and reduce the data, the background level of the detector. So I didn't prepare nothing about the details about the data processing, but this is quite simple case, and it's not comparable to higher energy physics, but it's also very challenging.
But for example, you keep every event that you see in your detector, you keep it. Then you can do a, or do you have to select a bit?
We have some trigger, yes. Mm-hmm. Once the event has gone over the threshold, our energy threshold is about 1 kiloelectron volt. So as soon as any particle producing some charge in the TPC goes above that threshold, then the electronics are starting to record the event. And then we register the charge as is driving to the readout plane, and then we use that to make a three-dimensional reconstruction in case of a pixel detector, and use that topology to validate with the calibration data of X-rays. X-rays is our signal. Actually, we do the calibration with the full telescope line. And there are different parameters that help us to fiducialize the data and to distinguish X-rays, real X-rays from other backgrounds. So our ultimate background are Compton scatterings on the detector that we cannot distinguish from real X-rays.
Thank you. Maybe John has a question.
Maybe I'll add this.
Yes, exactly.
Yes, add another question. So Javier, the Confront site you mentioned, this is in addition a new site in addition to DAISY, or this is really for low background study?
Yeah, I didn't go into much detail, but this is an independent facility. And we conceived this facility in order, because we expect to have different detector technologies. And we want to understand the nature of the background. So if it's neutrons, cosmics, by comparing with the data on other ground facilities. And at the same time, to test detector technologies at the same facility, so that we can directly compare. Yeah.
Okay.
Okay, thanks.
Thank you.
Good. So if I'm not mistaken, this concludes our parallel sessions.
Yes, this is the last talk.
Yeah. Don't know if you want to say a few words about the poster session, since you're going to be sharing that.
Yes,
as well.
yes, in an hour or so, yes. So I'm gonna stay up for this. So
yeah, there is a poster session with 4 posters in about an hour's time. You can find them, yeah.
Starting at 13:30 in the afternoon.
And the links are on the ICHEP agenda as well. Another thing that came to our attention is the panel, the discussion that is going to be chaired by Rebecca Gonzalez. I believe that is on Tuesday night, European time, and where there will be the chance to ask more questions or go into more detail with on the plenary talks that will be given. The Mattermost channel will stay open, so there can be threads for every single talk, so don't hesitate to ask questions even afterwards. And I think we're done for this morning. So thank you very much, and see you at the poster session.